各位来宾，下面将进入到我们今天大会的主旨报告。第一场报告将由邱院士主持，也请大家稍后。有请邱院士。
Now here we start the main thing. The first talk will be given by Andy Strominger, an old friend since I knew him in 1980 in IAS Princeton. He did not believe in Clavion at the beginning, then turned into the major founder of the whole subject, which has inspired me for the last 45 years. And I think the input coming from Witten, from Andy, from Martha, from everybody has been tremendous influence in mathematics itself. And I believe vice versa. So the interaction between string theory and mathematics has been tremendous. And it's still going on strongly. And I hope we pay all the attention to the major talks in this conference, certainly myself. And so Andy's talk, the first talk would be solved algebras in Minkowski, ADS4, DS4. Andy.
While we're waiting for that, I'd like to thank the City of Shanghai for their inspiring and wise support of basic research. I'd also like to thank my dear friend and inspiring colleague, Professor Yao, for organizing, I think the third time now, the Strings Conference. We miss him at Harvard, but he seems to be doing great things here in China. There's a very vigorous group now, including an organizer of this conference, who I'd also like to thank, my former student, Slava Lysov, who's been at on the faculty at SIMAS for 2 years now. So great things are happening in China, and it's a pleasure to be here. So I need something to change the slides. Okay, so in this talk, I'm going to talk about 3 recently appeared papers, all circling around the same subject of infinite dimensional soft or chiral algebras that appear in flat space, in ADS4, and possibly in de Sitter space. So one of the golden goals is universal realization of the holographic principle in any space. And we understand it very well in anti-Sitter space, but we would like to extend that understanding to Minkowski space and de Sitter space. Okay. I can. Okay, can you hear me? Yes, okay, sorry. So the very first step in finding a holographic dual pair is to understand what the symmetries of the situation are. Because the most elementary constraint on the dual representation of a bulk quantum theory of gravity is that it should have the same symmetries. And one of the things that has been understood over the last decade is that quantum gravity in Minkowski space has an infinite dimensional symmetry, which is called the loop group of the wedge algebra of W1 plus infinity, which can be understood and has been very concretely understood from multiple different perspectives. One is as an asymptotic symmetry in the spirit of BMS. The other is as the commutator algebra of a tower of soft graviton theorems, which originates in a Feynman diagram analysis. And in special cases, like so-called twisted holography, they can be understood as chiral algebras of a two-dimensional conformal field theory on the celestial sphere at null infinity. And actually their earliest appearance was, though it wasn't quite stated in this way, was as the deformation algebra of line bundles in twistor theory. And in fact, Penrose invented twistor theory for the purpose of solving self-dual gravity. And in that context, his solution essentially, though he didn't say it that way, amounted to discovering this algebra as it acted on the solution space and using it to famously generate all of the solutions of self-dual gravity. Now, it's a wonderful thing that we have these in Minkowski space, but we would like to relate Minkowski space to anti-de Sitter space, or we'd like to find out what they have in common so that we can import our knowledge of anti-de Sitter space to Minkowski space. And they seem to be completely missing in ADS4. Among other things, there's a mass gap, so you don't, naively, you don't have soft gravitons. Now, what we're going to see in this talk is there's a fifth way of deriving these, deriving these symmetries, and that is that they are the commutator algebra of light ray operators in the conformal field theory on the boundary of ADS4. And there's no contradiction with the mass gap in ADS because these things are not soft in the energetic sense. They're soft in the sense of boost weight, and there's a continuum there. And this all this work was inspired by a pair of beautiful papers which showed that this W1 plus infinity algebra has a very highly non-trivial deformation. So the parameterized by a parameter lambda. And these people use twistor methods. Taylor and Ju, there's an H missing there. Taylor and Ju used perturbation theory. Now, the W1 plus infinity algebra in flat space contains a global subgroup, which is the Poincare group. So it's a generalization, an infinite dimensional generalization of the Poincare group. And amazingly, if you add this term here, the Poincare group gets deformed. This algebra, the deformed algebra, also has a global subgroup, and that global subgroup is the SO42, which is, SO32, which is the isometry group of anti-de Sitter space. Okay, and there's also a de Sitter version of this. And so we would like to understand this in more detail. Now, I only have a short amount of time, so instead of talking about the details of the W1 plus infinity case, there's a simpler cousin of the W1 plus infinity algebra, known as the S algebra. And that's an infinite dimensional symmetry algebra, which acts on at tree level as on non-abelian gauge theory as it's the tower of soft theorems. It's generated by the tower of gluon soft theorems. Okay, so what am I writing here? So here, of course, if we're talking about a theory with a conformally invariant sector, later we'll discuss n equals Fourier-Mills. We have an SO42 algebra, which can be written in this way. It's got two SL2Rs. It's got translations. It's got special conformal translations. And then it's got dilations D. And this algebra is generated by a tower of soft gluons. And the commutator algebra of these insertions is this S algebra. And these generators here are labeled by a dilational weight P, which is 1, 3/2, 2, so on. And the leading term corresponds to Weinberg's soft gluon theorem. The Weinberg didn't actually discuss gluons, but it corresponds to that soft gluon theorem. And so it turns out that if you act with a special conformal transformation, this has been understood in various ways for a long time, you can actually generate this whole tower. So the slogan there is that Weinberg's soft gluon theorem plus special conformal symmetry implies the whole infinite dimensional S algebra. Now, so we want to relate this soft algebra in Minkowski space in this conformally invariant sector of the theory to something in ADS. So these are just modes. The soft gluons are just modes of the gauge field, and the gauge field, all the dynamics are conformally invariant. So we can conformally map Minkowski space to the four-dimensional Einstein cylinder, S3 cross R. And once we've done that conformal mapping, we can turn those modes. We can continue them over the entire cylinder. And since two copies of four-dimensional anti-de Sitter space is also conformal to the Einstein cylinder, we can look at the modes on Minkowski space and understand what form they take on four-dimensional anti-de Sitter space. And we find something very interesting. We find, first of all, you have to do the embedding rather carefully. If you take a point on the Einstein cylinder, the set of points, the region which is space-like separated from that point, comprise a Minkowski diamond on the Einstein cylinder. And if we choose that point to be on the boundary of one of the common boundary of the two ADS4s, then we get so here's the standard expression for one of these soft gluons. It's just the integral over null infinity, which maps to this region here of the normal component of the field strength. And now if we conformally map that to ADS4, we find that it becomes a light ray operator on the boundary on the three-dimensional boundary of ADS4. And this particular and it's important here that the light ray begin and end at the antipodal point. It began at any point on the boundary of ADS4, but it should end at the antipodal point. And with these particular boundary conditions, there's a conformal factor here, which I'm not working out, exactly this, now we use the ADS4 CFT3 correspondence, and we identify the normal component of the field strength as a current in the dual boundary conformal field theory. So now what we're learning is that soft operators in Minkowski space under this conformal map become light ray operators. In fact, this particular one is the most studied of all of them. They become a so-called light transform of global symmetry current in the boundary CFT3. Okay, so now these light ray operators, their commutators, take a very rich form, and they've been a subject of intense study for the last decade, and there's really a lot known about them. And it's actually quite non-trivial, not only that these operators exist, but that their commutators can be computed. So we get to import for free all that hard work. And there was one thing that they didn't do. Nobody ever asked the question, if we take this fundamental light transform on the boundary in a three-dimensional CFT, what if we take all of its conformal descendants under the three-dimensional SO32 conformal group? What is the algebra of those things? Well, the algebra of those things is exactly the S algebra. And that's a little more complicated to show than you might think, because you have to worry about degeneracies and so on. But so every CFT3 on the Einstein cylinder with a global conserved current has an S algebra whose generators are conformal descendants of the light transforms of the global conserved current that you always expect whenever you have a bulk gauge field. So this is now a very concrete connection between ideas that have been developed in trying to understand flat space philosophy and those ADS philosophy. Now, I told you before that Weinberg's soft gluon theorem plus conformal symmetry implies the full S algebra. But what about, so what if we just take a theory like n equals 4 Yang-Mills? So this is a theory with an S matrix. In the previous transparency, I was talking about a conformally invariant 4D gauge theory on a manifold without a boundary. But now we have an S matrix. And you might think that, and I thought for a moment that immediately we would get an S algebra for n equals 4 Yang-Mills because it's conformally invariant. But in fact, it's not quite conformally invariant. There's an anomaly under special conformal transformations. And that anomaly happens because special conformal transformations move the boundary of the Minkowski diamond in the Einstein cylinder. And so the very definition of the S matrix violates conformal invariance. Nevertheless, as many people in this room knows, but I'm sort of a bit of a newcomer here to this, there is a just incredible amount of detail known about the S matrix for n equals 4 Yang-Mills. And with my wonderful collaborator, Fernando Alde, we showed that even though this anomaly is there, you can define some an infrared safe variable, which we call the hard S matrix, which transforms in an undeformed representation of the S algebra. That is, the full quantum S matrix for n equals 4 Yang-Mills obeys an uncorrected S algebra. Now, this assumes a number of things about the S matrix which are commonly assumed in the literature, like the exponentiation of the one loop divergent part of the one loop divergences, and also the Wilson loop duality, many things, but we used all of that, and we were able to show that that the S matrix factorizes in this form. And there was one new thing, and that the soft thing contains all the IR divergences. And there was one new thing which we needed to prove, and that is that, so people have looked at splitting functions. There's exact formulas known for the splitting functions and for the ordinary soft theorems. That's pretty more or less known in the literature. But we also had to prove a non-renormalization for all loops for the half collinear splitting functions. Okay, now back to ADS4. I started out, I promised I would tell you something about the what time do I stop? Okay. Okay. So it turns out, so we expect an ADS to get this deformed W algebra. I told you about the S algebra. A little more complicated to get the W algebra than the S algebra because gravity is not conformal invariant. So if we want to do that map to the cylinder, we have to keep track of how the interactions transform. And I believe that we would get this piece if we did that, but we used a shortcut. It's also true, we just looked at the boundary CFT3, and we looked at the light transform of the stress tensor. Now, the light transform of the stress tensor is a famous and intensely studied object. It has a name. It's called the anek. And a few terms, a few commutators are known between the anek and various moments of the anek. And it turns out that if you take the anek and you take all of its three-dimensional conformal descendants, that a few of them have been studied, in particular in a paper by Cordova and Shao, an old paper by Cordova and Shao, and then there's been much more work done on it. And a few commutators are known, but just from those commutators and from the conformal algebra, you find that on the nose, if you take the anek and all of its conformal descendants, the commutator algebra of those is exactly this deformed W algebra. Now, in a way, that had to happen. And the reason it had to happen is that we know that whatever we get, well, it's not too hard to see that the anek generates one of the global symmetries. And therefore, it must be in a multiplet with 9 other currents that generate the rest of those global symmetries. And so whatever algebra you get, it should have an SO3, 2 global subgroup. And so we knew it had to work, though it was some work to show it, because this algebra also has an SO32 global subgroup. So the conclusion is that these soft chiral algebras that are showing up in Minkowski space were kind of right under our nose in de Sitter space, in anti-de Sitter space. And so every CFT3 on the Einstein cylinder has a deformed W algebra whose generators are the conformal descendants of the Anak operator. And in fact, that doesn't quite get it for you. You have to take the conformal descendants and then take their commutators. And so what about de Sitter space? So if we try to do the same thing in de Sitter space, so this is a question mark. I'm not sure I have anything very useful to say about it. We end up with an operator which is traversing de Sitter space from one point in the infinite past to the antipodal point in the infinite future, but integrals along geodesics like that are not in our usual class of allowed good operators, because this geodesic is no longer on a boundary. And what we did before, it was very important that we mapped something from the boundary of Minkowski space to the boundary of anti-de Sitter space, because only on the boundaries of space-times do we have good, well-defined, a lot of good, well-defined operators. So I'm not sure how I did on time, but that's the end.
Are there questions? Yeah.
I'm sorry, I can't really hear.
Oh, sorry. So to make this S algebra or this loop of W1 plus infinity algebra symmetry, it should act on the Hilbert space faithfully. So is there a proof for this fact, or?
You mean as a symmetry acting on the Hilbert space? No. It's a good. I mean, this is all very new, but that's I think a very important thing to do, to see if that can be understood as a symmetry acting on the Hilbert space.
Very pretty. Is this generalizable beyond 4 dimensions?
I think so. I have an affinity for 4 dimensions, but I think that yeah, it should work in. Should certainly have analogs in higher dimensions. The things, it's funny, these different approaches to these algebras have different positive and negative points. And the thing that obviously happens in higher number of dimensions is there's obviously soft theorems in higher. And so since those are there, there's got to be some meaning to them.
So in n equal to 4 super Young Mills, these ANEC operators obey an interesting operator product expansion. Is that included in this S algebra or W algebra?
In n equals 4 Yang-Mills, you wouldn't be, I mean, that's a gauge theory, not a gravity theory. So we wouldn't be looking for generators of W1 plus infinity. We would just be looking for generators of the S algebra.
Other questions? Yeah.
Thanks for the presentation. I was wondering, you were pointing to these kind of operators and you had integrals. Do you consider them as non-local operators, or you can build both local and non-local operators?
Oh, can I get the screen back? Okay, so it's important that those operators were on the boundary. And so if you just had an integral of a non-abelian field strength along some null geodesic in the bulk of the space-time, it wouldn't make much sense. But soft operators, in 4 dimensions, the soft operators can be written as integrals of null infinity of a null geodesic. And that makes sense because when we talk about the S matrix in a non-abelian gauge theory, we fix a color frame at the boundary.
Thank you.
Okay. Other questions?
And that's the step that fails in de Sitter space.
Right.
Hi, thanks for the beautiful talk. Is the S algebra a symmetry of the twistor string, and where does ADS3 sit in that context?
All of these algebras are symmetries of, as far as I understand, of everything in twistor space, in various twistor self-dual constructions. Probably it's a symmetry of the twistor string. I haven't studied that, but one of the things that I think is most interesting about this is that for a long time there was a fear that these infinite dimensional algebras could not escape the domain of integrable self-dual theories like self-dual gravity. And here we see, using all the wonderful things that are known about ADS, we see that these algebras can exist in strongly coupled quantum systems.
So in the gravity sector, it has to be a different algebra because, as you said, there's no conformal invariance, whereas in the twistor string, there is conformal invariance. So the algebra you're talking about is the one for gravity, not for conformal gravity. So perhaps there's another algebra, which is the one relevant to the gravitational sector of the twistor string.
Well, in conformal gravity, is this the twistor string with conformal gravity?
So in the gravitational sector of the twistor string, the one defined by Witten, there is conformal gravity, not ordinary gravity.
Yeah. So interestingly, there is and this is just were to appear with Simon Fraglin and Robles. Many of the twistor people understand this already. There's a bigger algebra, which we call CW1+, which you can get by taking SO42. You start with the W algebra, and you take SO42, and you enlarge it by that. And that's actually a very simple algebra, and all these other algebras are more complicated subgroups of it. So that's like the really nice thing in twistor.
Yeah.
Thanks for your talk. So I have a question for the N for super youngness. So how do you deal with the anomalies in the N for super youngness?
How did we deal with them?
Yeah, because in the conformal map, the conformal anomalies were in phase factor.
Right. So the way we dealt with them, and I feel there must have been a better way to do this, but it's only an anomaly in special conformal transformations. And but we just brute forced it. These anomalies are pretty controlled, and they're largely driven at one loop, and we just showed that you can define this A hard by factoring off it's long been understood that there's this BDS prefactor which Byrne, Dixon, and Chernow, and you can exponentiate that. It's supposed to, the one loop anomaly is supposed to exponentiate and contain all the higher divergences. So we strip that out in a very careful way and then analyze the structure of the poles. We were motivated to do that because it was it's hard to understand how you could have this algebra tree level and then have it, what would it mean if it were explicitly broken? So it seemed like it should be there in some form, and you can't really deform it. These algebras are hard to deform. One thing I want to stress, though, is the difference between soft algebras and soft theorems. The soft algebras are the commutator algebra of the soft theorems. And the soft theorems certainly get corrected. They're subject to some integrability constraints from the soft algebra, but they get corrected by some, at every order, there's some finite list of higher dimension operators that can correct these soft algebras. So these non-renormalization theorems are all about the algebras. Same thing for W. And the theorems themselves, we're expecting they will get correct.
Thank you.
Okay, let's thank Andy for this beautiful talk.
All right, so we are going to have the second talk of this morning session. Okay, so I'm very honored to introduce Wei Song. She's from the Yao Mathematical Sciences Center at Tsinghua University, and she will talk about operators and correlators in TT-bar deformed conformal field theories.
Thank you. So this is actually the third time I'm attending strings conference in China. 20 years ago, I was a PhD student in Chinese Academy of Science. I was a volunteer. 10 years ago, I was a faculty member at Tsinghua University, and I was one of the organizers. So today I'm speaking here. I really want to thank the organizers to give me this opportunity. Appreciate this opportunity. Thank you. So today I'm going to talk about operators and correlators in TT-bar deformed conformal field theories in 2 dimensions. Let me start by recall what is TT-bar deformed theories. It is defined from the flow equation also. Is there a pointer? Oh, never mind. So it's defined, so the Lagrangian, the derivative of the Lagrangian with respect to the deformation parameter is proportional to the determinant of the stress tensor of the theory. So lambda here is the deformation parameter. It has a unit of length squared. So this is an irrelevant deformation. So the theory is interesting for many reasons. It can be defined very universally as long as the theory has translational symmetries. And it is solvable. The spectrum on the cylinder can be just expressed in terms of the deformation parameter and the undeformed spectrum. And the scattering amplitude can also be obtained from the undeformed ones by addressing by a CDD factor. And the deformation also preserves many of the interesting properties of the undeformed theory, including this modular invariance and integrability. And it also allows for various interesting reformulations and also generalizations. To me, the most fascinating aspect of TT by deformed theory is that it is useful in constructing holographic dualities beyond the standard framework of ADS-CFT correspondence. So this is useful in both the bottom-up approach, where you can probe the interior of the ADS spacetime, and also in this top-down approach, where you can start with known examples of ADS-CFT correspondence built from string theory, and then doing the deformation, and you will engineer a very explicit model of actually holographic correspondence between single tree TT by deformed CFT and string theory on this linear dilaton background. In a sense, this is a concrete model of flat holography in 3 dimensions. So what are we going to learn more today? Broadly speaking, we'd like to understand the basic data of the TT by deformed CFTs, how they are organized, and what are the physical quantities we can compute. And for holography, we want to make further progress on identifying the holographic dictionary. So we are going to talk about operators and correlators. I will introduce a new type of operators. It has many interesting and nice features, and the correlation function can be controlled, and actually conformal symmetry can be used to organize the computation. So this work is mainly based on these 2 papers in collaboration with a great team in Tsinghua. So Liang Yuchen is a postdoc. Zheng Yuandu and Kang Ning Liu are both PhD students. Both Zheng Yuan and Kang Ning are giving gong shows. And today I'm going to focus on TT by deformation. If you are also interested in JT by deformation, go to Zheng Yuan's gong show talk. And also Kang Ning will be on the job market this fall. Please pay attention. So let me start. So as I mentioned, we are interested in finding a good basis of operators. So we will discuss this, using this Hamiltonian formalism, and I will talk about 3 candidate operator bases. The first candidate is the most naive and the most straightforward one. If you consider any CFT operator on the t equal to 0 slice, and then evolve it by the deformed Hamiltonian, you define the so-called undeformed operators. So we will denote such operators by O0. So these operators are very natural. That's basically what you will first try when you do, say, canonical quantization. The drawback of this type of operators is that it is very difficult to do computations. For instance, if you try to use perturbation to calculate the correlator, so as long as it is beyond the first linearity level, you need to also modify your stress tensor, because the stress tensor is instantaneous. You cannot just use the CFT stress tensor. So it's out of control. Each order, you need new data. So then comes the second candidate. This is the so-called dressed operators. We use O tilde to denote them. So they are defined by the solution of this flow equation, d lambda, which equals to ordinary derivative with respect to the parameter lambda minus I chi, the commutator with chi to it. So why is this useful? So as we know, if we consider this TT-bar deformed theory on a plane, then the deformation itself can be understood as performing a canonical transformation, and this operator X is implementing this canonical transformation. So because of these properties, these dressed operators, they have very nice features, because if you start with CFT, you have Virasoro times Virasoro symmetries at the beginning, and this canonical transformation will help you to build Virasoro times Virasoro generators even after the flow. And you can also consider as primary operators before turning on TT-bar deformation, and this TT-bar flow will also allow you to solve this this flow equation, and there will be a dressed version of primary operators. So all the dressed operators, dressed stress tensors, they will obey basically the same properties as the undeformed CFT. In particular, they have the same correlator. So the dressed primaries, the two-point function is super simple. It's just a power law. And you will keep the wide identities and all other things that is controlled by conformal symmetry in a CFT. So this is all good, but there is a price to pay. The price is that if you try to solve this equation, you will get a highly non-local operator. Let me show it very explicitly. So it's from this slide, you can see a very messy formula. So let me explain. O tilde is this dressed operator, and on the right corner, this O naught is the undeformed operator. So they are related by a complicated infinite sum. And there is in the sum, there's also this appearance, this delta U hat. This is the integral of the stress tensor. So from here, you can explicitly see that this dressed operator is manifestly non-local. So it's we know the correlator is super simple. The problem is that we don't know what this quantities you calculated is really related to the deformed theory itself. So in short, the two aforementioned two candidates, they all have the disadvantages. The undeformed one can be defined at each space-time point, but the computation is difficult. The dressed operator obeys symmetry properties nicely, but they are highly non-local. So we want something that has the advantages of both operators, but don't have these disadvantages. The third option is already here on this slide. If you can see, between the dressed operator and the undeformed operator, there's a bridge operator. This I colored in pink. this O operator. It serves as a bridge between the undeformed and the dressed operator. From the second colored box, we can see this pink operator O is related to the undeformed operator by multiplying by some factors that depend on the stress tensor. So this new operator is also defined at each point in space-time. So it has some flavor of potentially a local operator. On the other hand, as we can see from the first expression, so the dressed operator and this O operator, they are related by infinite sum. But if you look at the infinite sum, it looks like some sort of Taylor expansion. So then it's just that maybe if we try to write this pink operator in terms of the tilde operator, maybe we get something simple than this. So we will focus on this pink operator. And for in this talk, let's just refer this new operator to physical operator. And it has the feature that it's pointwise defined, and it has, as we will see, it has better symmetry properties. So as I mentioned, it can be actually written in terms of this tilde operator in a very simple way. It's integral O tilde with this delta function. So there is a very nice interpretation in terms of this string theory formulation of TT by deformation. So we can consider there is a string worksheet. Where this O tilde operator lives on, and then the TT by deformed theory really lives on the string target space. So this delta function is actually a mapping from the string worksheet to the target space-time. And what the delta function selecting is actually the map, basically a classical solution, and this solution is actually just the inverse transformation of this non-local coordinate. So this will be yes. So that's this our physical operator, and this the delta function will actually choose the solution, which is just relating ordinary coordinate to this so-called non-local coordinate. This non-local coordinate usually plays many important roles in this TT by deformed theory. Our discussion is in this Hamiltonian formalism. You can also consider this TT by deformation in this formalism of topological gravity, and where Aharoni and Barrow studied. So at the classical level, it's the same operator. So okay, so far this physical operator can be written in two equivalent ways at the classical level. And now we need to promote it to the quantum level. So then there are two routes. One is to promote this expression in terms of the undeformed operator to the quantum level. But this expression is nice in the sense that all the right-hand side are operators defined at a point. And there's no integrated quantities. So and also this operator has the property that if you look at the boost transformation, it has fixed the boost charge. The undeformed operator itself doesn't have a nice boost transformation property. And also, if we apply this flow operator, d lambda, to this physical operator, it's also simplifies significantly. It's just a total derivative. So these are all nice features of this expression. But the drawback is that, as you see, that the operators appears in the denominator. So if we want to promote this to the quantum level, there is always the ambiguity of how to do the normal ordering, and that's difficult. Alternatively, we can also write this physical operator in terms of this O-Tudor operator, which has very nice conformal symmetry properties. And this is an expression in the momentum space. This expression is also very nice. As you can see, that the only effect of the deformation is in this exponential factor is e to the lambda integral of the stress tensor. Everything on the right-hand side are just these stressed operators. They can just be willed as CFT operators. So this is like a very line-like dressing. And everything here on the right-hand side just can be organized in using conformal symmetry. So that's our choice. So we promote this expression to the quantum level. So we assume that this dressed operator, they always exist. And then you build such an operator and then study all the properties of that. So that's the step from classical expression to quantum expression. So that's our definition of this operator at the quantum level. So here is a summary of the 3 candidate operators in this Hamiltonian formalism on a plane. And I hope I convinced you that this newly introduced physical operator indeed has some nice feature, and let's just focus on that and go ahead and do some computation. So the strategy is very simple. As I mentioned, so the momentum space expression, the right-hand side is purely in terms of this Tudor variables, and their correlators and what identities are exactly the same as in a CFT. So we insert this operator into the correlator. Then what we are going to do is just to expand this exponential, and then we can do conformal perturbation order by order. And at each order, what we are going to do is to repeatedly use the wide identity. And in principle, you can do this at every order, and every order, the result is known. You have fully controlled. And then you can just sum it over and get a final answer. So this is fundamentally different from the computation of this undeformed operator, where if you try to do perturbation, it's out of control. So here is the computation, and there is so there is a way to organize this computation, and we can actually, there is always a very universal piece, that's the leading log piece in both the momentum position space and the momentum space. And you can just carry out the sum, and the result in momentum space is super simple. It's just this 2-point function in momentum space for a CFT. The only difference is that you replace the conformal weight to h plus lambda pp bar. So that's the result in momentum space, and this is various approaches has confirmed this result, and it satisfies the Cullen semantic equation derived by Cardy, and this formula first appeared in this string theory computation on the worksheet, and this is to based on this TST-TD bar correspondence designed for this holography for linear deleton background. So, and with this result, then let's see what we can learn from these correlators. First is the UV behavior. If we take the very large momentum limit, that will probe the deep UV. So we will see that there is the growth is exponential in the momentum. So usually in local quantum field theory, we will expect parallel, but in this case, it's an exponential. And the result interpretation depends crucially on the sign of lambda. So if the positive sign, that's the usually called this unitary sign choice. In this case, this UV behavior is soft, it's exponentially surprised. Whereas with negative choice of this sign, this it's exponential growing, and that sounds like a UV catastrophe. And we can also do a Fourier transformation of our momentum space correlator, and then it can be written in a very suggested way with this its Haidt kernel expression. The right-hand side, this G0 is the undeformed correlator, and there's an integral against this kernel. The kernel really looks like a Haidt kernel, but except that the parameter t is not a constant, but it depends on the position x. So this is reminiscent of this integral representation of torus Cartesian function. And we can also say that this formula also satisfies some very interesting flow equations. The first one relates the flow of lambda to some drifting and diffusion differential operator, and the second one relates the derivative with respect to this conformal weight as well. So then you can just study this differential equation system, and you will find that apart from the perturbative result we have, there is also you find some instanton-like contributions, and one is real. And to study this instanton more clearly, we can also go to this position space where the leading log terms can be directly summed in position space, and it's Fourier resummation, and along this contour there is a branch point. So as long as this combination C, which is log x over x squared, if it is positive, and then you will find a discontinuity. So what's the meaning of this discontinuity? So that's the last page. So if we the previous result is in Euclidean space, we can do an dual continuation and get a Lorentzian space result. From there, we will see that the punchline is that this is related to macro causality. If you consider positive lambda, and if you consider space-like separations, normally you will expect the commutator to vanish, but in this case, because of this discontinuity, we'll find that this commutator will not vanish. Instead, there is a non-perturbative violation of macrocausality. It's weaker at large distance and weaker at small lambda, but it is all there up to certain cutoff scale. So that's all I want to say, and I just stop at this summary slide. And thank you.
Thank you very much, Wei. So we have a few minutes for questions. Juan.
If the theory has a holographic dual, do your operators have a simple description as bulk operators at some specific points?
The holographic dual is a string theory.
Well, usually people say that when you do TT bar deformation is somehow related to putting boundary conditions at some fixed location. Is there a simple description of the operators?
Okay, so this cutoff picture is only valid for if you only consider pure instant gravity. So if you add matter, so it's not like you impose directly boundary condition to the matter. So it's more complicated, and I don't know a simple explanation of this operator.
Okay, thank you.
So thanks for your nice talk. You say that in classical level, the TT bar deformation is a irrelevant deformation, and JT bar is marginal. My question is possible to define a relevant deformation, a solvable relevant deformation in classical level and find the Lagrangian or not?
Maybe you are an expert on that. So I'm currently only focusing on these TT by JT by definitions.
Okay. Hello. I have a question that I see that you have left and right Hamiltonian. I'm not sure if there are some symmetry in your TT operator.
So the TT bar deformation, the left and the right, they are similar.
They are similar.
Yeah.
Can you briefly comment on the negative deformation parameter when the spectrum become imaginary and the behavior of two-point function and the physical operators?
We can define the physical operator for both positive lambda and negative lambda, but the UV behavior is opposite. It looks like the two-point function is growing as exponentially. So it sounds like maybe there's some UV disaster, and this is also like compatible with the fact that when lambda is negative, if you consider theory on a cylinder, then the high energy spectrum will become complex. So maybe it's fitting together, but I think at the moment we don't have a convergent decision about how to will the high, the complex spectrum or high energy behavior is negative.
Do you think that newly development of techniques such as resurgence can improve our understanding of these behavior?
Well, I think this instanton lag behavior is related to this resurgence.
Okay, thank you.
Okay, another question.
Could you please briefly summarize for us what we know about the holographic dual of this and how this work bears on it, of the TT bar deformed theory?
Okay, then maybe let me say there's let me see. I have some backup slides. See, oh dear. Oh no. Oh, maybe I just say it. So there is this bottom-up approach. That's the duality for this double trace TT by deformation. There are two proposals. One is by Verlinder and al. The proposal is that for, at least in the case for pure Einstein gravity, the TT by deformed CFT correspond to imposing directly boundary condition in the bulk. And then in that case, they can match this flow equation of TT bar to this the Hamilton-Jacobi equation, and also say if you look at the black hole entropy, and it also matches the this modified Carty formula from the field theory set. And there is related this more refined version of the double trace TT bar holography that's proposed by Monica Buka, and it relates this to impose mixed boundary condition to the gravitational theory. That is more general. It applies for TT bar deformation with both signs, and also you can add matter to that. That's roughly the story for this double trace. And then there's also the single trace version. So there, the single trace is defined only for very special CFTs where you have the symmetric product structure. You first do ordinary TT bar to the seed CFT and then do the symmetric orbifold. So if you consider type 2B string theory supported by NS flux, and then you can the single trace TT bar is correspond to this linear dilettone background, and this is also related to perform a TST transformation to the string theory. And there you can also work out the spectrum, the perturbative spectrum of long strings from both sets, and they match precisely. And you can also work out the black hole entropy from the bulk that also matches from, with the this Carty formula-like computation. And then this for this correlator, this field theory computation of the correlator, the momentum space two-form function also matches with the string worksheet computation. So that's so far.
How to apply? Okay. So I think we have to stop here because the schedule, otherwise we're going to be late. I suggest you ask further questions to Wei during the break. Let's thank Wei for her beautiful presentation. So we can enjoy a break, and we will resume the session at 11.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
How do I go back?
Okay, so I think we can start the first review talk of this conference. So it will be on a subject that has deeply influenced our understanding of quantum gravity and the path on the gravitational path integral. So I'm very happy that to introduce Zhenbing Yang from the Institute for Advanced Study in Tsinghua University. And so he will talk about quantum chaos and wormholes.
First of all, I would like to thank the organizers and the International Committee for the chance for me to present this review talk as streams. I'm going to give a review about the connection between quantum chaos and wormholes in gravity. This is based on many people's work, including those in the audience, and my understanding of this work. The subject of quantum chaos studies how generic quantum many-body systems can thermalize and develop random matrix statistics. In the context of black hole, this phenomenon becomes a geometric statement about the black hole horizon, its scattering, near-horizon scattering, and effects of wormholes. I will review 4 examples of this connection, and then the puzzles associated with wormholes. So this is the plan. Let's start with the canonical Pachin function. It can be understood as a Euclidean path integral on a thermal circle. If a black hole dominates the canonical Pachin function, then it will fill in this thermal circle with a smooth disk. Then the basic claim of ADS-CFT is that the Euclidean gravitational path integral on this geometry should satisfy all the axions of Euclidean quantum field theory on the boundary. That means it should satisfy refraction positivity, KMS, and continuous time transition invariant. That allows us to cut the thermal circle into 2 halves and understand this canonical Pachin function as an overlap between a state living in the Hilbert space, double Hilbert space of H tensor H star, where H is a CFT Hilbert space. We will call this as a thermal field double state. Under weak rotation, the Euclidean disk gives us the Lorentzian eternal black hole geometry. And the thermal field double is also sometimes called the Hartle-Hawking vacuum. The thermal field double state is invariant under the boost symmetry. Here, the boost killing vector K can be understood as the Lagrangian limit of the energy difference between the left system and right system. So this is a basic setup. Now let's consider a simple quantity, which is a late-time 2-point function, thermal 2-point function. The late-time thermal 2-point function could be understood as an overlap between a single particle state W in the two-sided Hilbert space with overlap of its image under the boost evolution T. If we have a classical mixing system, then such a 2-point function should dissipate exponential decaying behavior controlled by the Rouleau-Poricot resonance. In gravity, this 2-point function, a latent decaying of the 2-point function will be controlled by the black hole quasi-normal frequencies. The black hole quasi-normal frequencies can be understood or defined as the eigenvalues of a modified boost operator. Here, K is a boost isometry of the thermal field double state, and we can define another symmetry generator G locally near the killing horizon. The thermal field double state will be a vacuum with respect to the this generator G. G is a local Minkowski Hamiltonian at the King horizon. So this deformation makes a boost operator non-Hermitian, and its eigenvalue gives you the quasi-normal frequency. A simple example of this quasi-normal decay is to consider thermal two-point function in ADS2. Then, based on the conformal symmetry, you can uniquely determine the two-point function have this Cauchy behavior with controlled by the scaling dimension delta. And if you expand this two-point function at late time, we see a sum of exponential decaying contributions. Those are the quasi-normal modes in the ADS2 black hole. If we have a more general black hole, we should expect it to replace this sum as an explicit series of the quasi-normal frequency of the black hole geometry. A simple understanding of this exponential decay, a geometric understanding, is to consider the heavy operator limit. Then the two-point function could be understood as a linear growth of the Einstein-Rosen bridge in the thermal field double state. So here we do an alternative view of this two-point function as measuring the correlation length between the two-sided geometry as a function of time. So this is the first example I want to discuss. How thermalization of the two-point function is related to the quasi-normal frequencies and the rows of the Einstein-Rosen bridge. Now let's come to our second example. We've defined the thermal field double state, but the state itself is actually unstable despite the name of the vacuum. It is unstable due to early and late perturbations. A standard diagnostic of this instability is a so-called regularized out-of-time order correlator. It evolves the system forwards in time, insert operator, and backwards time, and forwards and backwards again. One way to understand this OTOC is to think of it as evaluating the measuring the correlation equal time correlation length in the perturbed single particle state under boost evolution. For a generic large N system, this OTOC will be after thermalization scale, after thermalization time will stay a constant for a long time, of time proportional to log of the degree freedom of the system. And after that, it should start grow exponentially. And that's that indicates the instability of the thermal field double under perturbations. And after the scrambling time, the time scale when it starts to develop this instability defines the scrambling time of the system. And after the scrambling time, this OTOC should exhibit exponential decay, just like the quasi-normal decay of the two-point function. The rate of the exponential growth with lambda L defines the Lyapunov exponent, and it satisfies a universal chaos bound 2 pi over beta that is saturated in Einstein gravity. One way to understand the exponential growth of the OTOC in gravity is to view it as an overlap between two different order states acting on the thermal field double. So it can be understood as an overlap between an incoming state where we act on W in the past and the V in the past. And then look at the S matrix between this incoming state and outgoing state where you act on V on the left and W on the right in the future. And because the time evolution becomes a boost symmetry, near the horizon, at late time, this V and W particle will receive high energy scattering at the horizon. And in gravity, the leading force dominates the scattering is given by the shockwave mode. That could be understood as the retarded and advanced scrambling modes for a generic chaotic system. And the J to Hooft's shockwave S matrix will be proportional to the center of mass collision, and that gives you the exponential growth of the OTOP. That's the second example I want to discuss, how the near horizon scattering leads to the exponential growing of the out-of-time order corridor. I want to stress that here we see two time scales in the system that can also be defined for generic many-body chaotic system. One is the thermalization time scale, can be probed by looking at the two-point function, and another is the scrambling time. And we will use these two time scales in the next part. Are there any questions? Okay, now let's go to our third example. We've studied the behavior of the thing at different time scale of these simple correlation functions in the thermal state. But quantum chaos also require that if we look at the system at longer time scale, it should exhibit random matrix behavior. And more precisely, the BGS conjecture states that if you have a classical chaotic quantum system, then if you look at the local spectral correlations, then it should satisfy random matrix. It should agree with the random matrix prediction within the same symmetry class. The energy scale controls this behavior, define the Thoros energy. For example, if a system does not have any discrete symmetry, and that defines the Gaussian unitary ensemble, then the connected spectral correlator should have this universal sign kernel formula. And if you look at the energy separation bigger than the inverse level spacing, here rho is a spectral density. Then this spectral correlator, connected contribution to the spectral correlator, should exhibit this power law correlation. That's called the spectral rigidity. One can also define a Fourier transformation of this spectral correlator to define the spectral form factor. And then the spectral rigidity transforms into a linear ramp. Depends on the parameter of T. And that's the definition of the spectral form. The spectral form factor, one way to understand the spectral form factor is that you can view it as a trace in the double Hilbert space with a boost up evolution operator. Then we already see that the thermal field double state itself is invariant under the boost. So that means that state will survive under the trace. But we can also consider summing over states nearby the thermal field double state and consider their contribution to the spectral form factor. And geometrically, if you start with the thermal field double state and we boost it and go trace it back to the original thermal field double state, that gives you the so-called double cone wormhole discovered by Schenker Stanford. But in fact, you have to do a little bit more complicated than just simply act on the boost isometry. That's because at the horizon, it's a fixed point of the boost symmetry. So literally taking a quotient of the thermal field double with the boost isometry will lead to a singularity near the horizon. So one way to fix that issue that discovered by Schenker Stanford is to go around the singularity in the radial direction near the horizon. And because locally you have a killing horizon, and you can define, so it's given by the Rindler space, such a continuation of the radial coordinate in the complex direction is universally defined for any for any killing horizon. And effectively, that turns this trace of the boost evolution to the trace of the modified boost evolution, k tilde, that was defined for the, that is what we use to define the polynomial frequency. If you sum over states nearby the sum of your double state, namely you can consider acting on, consider bulk excitations on top of the sum of your double state, those summation in the trace leads to a trace of the bulk fields with the boost evolution operator. So that leads to a solution of the Einstein equation with two asymptotic boundaries. If you evaluate the classical action of this unshelled solution, then you won't find the classical action of this wormhole vanishes. So it's an exponential small contribution compared to the thermal partition function. Now, if we consider the one loop partition function around this double cone, we can find zero modes. One way to understand this zero mode is to notice that we have a family of states that are invariant under the boost. The sum of your double state certainly is invariant under the boost, but you can also evolve the sum of your double state with boundary Hamiltonian. Those will still be invariant. And you can also consider sum of your double state of black hole with different energy. Those give you two families of zero modes in the path integral. Geometrically, the relative time evolution with tau parameter can be understood as a twist parameter on the double cone, where if you start with a t equal to 0 size on the left and going to the right, they may undergo a relative boost. It's kind of like holonomy that can be measured by looking at the two-side geometry. So this gives you two family of zero mode integral of the one loop partition function. But because we've taken the quotient of this geometry, of this eternal Panel's diagram, one of the twist integral is compactified to the range from 0 to capital T. And that leads to a linear in T growth of this double cone geometry. T is a parameter that enters in the definition of the spectral form factor, the Fourier transformation parameter. And the energy integral is an honest zero mode integral. One just define the path integral by restricting the range of the energy. This result precisely agree with the random matrix prediction, including the one of the 2π numerical factor. Of course, we also need to consider other contributions on top of this one loop integral. For example, states that nearby the sum of a double state by inserting matter excitations. Those contributions can be thought as a trace of the Bach-Hilbert space of the quantum field theory on the wormhole geometry. One way to understand that expression is to notice that the double cone geometry have a topology of a cylinder. And then if you do a canonical quantization as a QFT, by slicing this the cylinder horizontally, that gives you a trace expression with a boost evolution operator. We've already said that we've already said that the eigenvalue spectrum of the modified boost operator is complex, that give you the quasi-normal decay of the two-point function. So that means this trace exhibit exponential decaying behavior, and at late time it should be dominated only by the Booth invariant state, the zero eigenvalue state of this k tilde, which is nothing but the vacuum wormhole, the Hartle-Hawking vacuum. And we have already taken that into account in the zero mode integral. So that means, at that time when the bulk trace is dominated by the vacuum determining the Thoris time scale of the system. And we see that it is controlled by the quasi-normal frequency of the system. And the slowest decaying mode, namely the quasi-normal frequency with the smallest imaginary part, controls this time scale. And that determines the Thoris energy of the system. This is my third example. So here I want to say that before we see two time scale, the thermalization time scale control the two-point function decay and the scrambling time scale. For this double cone wormhole geometry, we only see one time scale entering the game. That is the thermalization time scale, and that determines the time scale for us to see the spectral rigidity. To see the spectral rigidity. And in gravity, that is beautifully explained by this universal double cone wormhole construction. But spectral statistics is not the only thing you can consider in a generic chaotic system. There are also information about its eigenvectors of the Hamiltonian. One way to probe those eigenvector statistics is to consider the matrix element of a simple operator O with its energy eigenstate. You can write this matrix element separate the matrix element into the diagonal form and off-diagonal form. Then the eigenstate thermalization hypothesis claims that for a chaotic quantum system, this matrix element should have a smooth behavior in the diagonal form, smooth behavior in its diagonal matrix elements, and also a smooth behavior in its off-diagonal matrix element times a random phase. So all the erraticness of the matrix element are encoded in this RMN, which is a phase that is random in MN indices. Here, S is the entropy of the system, and G is the order one smooth function that capture the quasi-normal frequency of the operator. So ETH then claimed that this random phase RMN should essentially behave like a Gaussian random variable. How do we see this ETH statistics? One way to consider the statistics of RMN is to consider the late time two-point function. Here we consider different operator V, the overlap between two different operators V and W separated in a time evolution T. Then if you put in the ETH on that, that predicts exponential small but non-decaying T contribution to the two-point function square. That comes from weak contraction between the random phase associated to W and its compressed conjugation and V with its compressed conjugation. How do we understand this ETH statistics in gravity? Here we will use the same logic to construct double cone that S did for this two-point function. That is, we can write this two-point function squared as a trace in this double Hilbert space. Then we can consider the contribution to this trace from the thermal field double state. That means we start with a thermal field double state and measuring the thermal field double state with operator WL, WR. Because the thermal field double state have a short wormhole length and strong correlation between the two sides, if you perform such a measurement, we'll return back to the original thermal field double state with high probability. And such state is invariant under the boost. So after the boost, we still get a short wormhole. And then you can measure the V again, which still give you high probability of the short wormhole geometry that is invariant under the boost. So that allows you, and then that allows you to trace back to the initial state. That gives you a large contribution to this trace. The resulting wormhole is a so-called, I will call it an ETH wormhole. Because of the relative boost separation between V and W, these two pair of particles have a large relative boost separation between the two sides, and those generate those will be very close to the horizon, to the past and future horizon, and that generates a large null momentum. But importantly, although it doesn't look obvious from this figure, these two pair of particles do not scatter with each other. Otherwise, this geometry will become exponentially small because of shockwave scattering. Compare with the double cone wormhole. Here, the new ingredient, we have two new ingredients. One is that this wormhole contains operator source kicks coming from the operators. And that the second ingredient is that we have both forward and backward evolution. In fact, it is very important, due to the second ingredient, it's very important that we have this operator source. Because if we don't have those operators, then the forward and backward boost evolution will just cancel each other. In the end, we'll have a wormhole with, we'll just have a zero wormhole with a zero boost evolution. And effectively, we get a trace of identity that leads to a divergent answer in the larger limit. Yeah. So this is my next slide to explain this importance of the kick. So when we have this operator insertion, for example, the W particles that created in the past horizon, then under the boost evolution, this W particle will source the retarded scrambler mode or the shock waves. And after a scrambling time, this scrambler modes will decorrelate between the forward and backward time evolution, just like how the thermal field double state is unstable due to early perturbations. And that takes a scrambling time. Similarly, the insertion of a V particle also excites a backward scrambler mode, that backward shockwave modes that decorrelate between these two forward and backwards boost evolution. And after a scrambling time, these two boost evolution becomes effectively independent, and they no longer cancel each other. This leads to a net boost evolution time on this wormhole geometry that is 2 times the total boost evolution minus the amount of scrambling time that take to trigger the scrambler modes. And this boost evolution effectively will display the same quasi-normal frequency decay as the case on the double cone. And it takes the same Thoris time scale for this wormhole to become stable and approach to its asymptotic value. And that adds up to the time scale for this wormhole to approach to the random matrix prediction that's coming from the ETH ansatz. And we see how the scrambling time enters to give us a new time scale. This is a bulk prediction of how ETH ansatz become valid. So this is my fourth example. How am I doing with time? Okay. Now let's. Now I want to discuss some applications of the wormholes. So I'm already summarized 4 connections between quantum chaos and wormholes that I want to discuss in detail. So for the application, I'll be short. So one application of wormhole to understanding puzzles in quantum gravity is that it plays a role in understanding the late-time behavior of a Hawking variable of the late-time behavior of the Hawking radiation, the entropy of the Hawking radiation. If we have a unitary system, then the von Neumann entropy of the Hawking radiation should goes to 0 at late time when the black hole is fully evaporated, but it should also grow at the beginning. So this shape gives you the page curve of the entanglement entropy. And it is discovered recently in 2019 that wormholes can contribute to the calculation of the von Neumann entropy of the Hawking radiation that leads to a decaying behavior. Another application of this wormhole effect in the black hole information paradox is that it also contributes to the late-time non-decaying behavior of the 2-prime function. So so we've already said at the first example that if we just consider the behavior of 2-prime function on the sum of the double state, this 2-prime function exhibits exponential decay given by the quasi-normal frequency. But if one have a system with a discrete energy spectrum, then the 2-prime function at late time should not be 0, but approach to a non-particularly small constant. And in fact, if we use ETH on that, when expected at a time scale called E prime ETH, where you can forget the correlation between the energy eigenvectors and the energy spectral and the energy eigenvalues, then the late time 2-prime function should exhibit the same behavior as the spectral form factor. So a combination of the double cone wormhole and the ETH wormhole in a smart way can give you the linear ramp growth of this 2-prime function. And in the context of JT gravity, which is a simple model in 2D quantum gravity, this is discovered by Phil Saad. There are also more speculative application of wormholes to understand firewalls in typical state black holes. Here, the proposal is that wormholes can create, sometimes wormholes can create firewalls for certain bulk observers, interior observers who jump into the black hole. So that's all I want to discuss about the good things that wormhole brings us. Now, I want to go to the puzzles associated with wormhole. I want to pause if there are any questions for the first part. Yeah. Yeah.
The BGS conjecture and Polyakov resonances. But these things require more than just chaos. They require global chaos or hyperbolicity. So I was wondering, do you have any intuition for what that means about the bulk?
Right. So one way to understand this, I think in the gravity, because of the Lyapunov growth, you should think about analog in classical chaos is globally hyperbolic, right? Which is tell you that if you look at the perturbation, they have the Lyapunov mode, and it's universal, like uniform on the phase space. But it's not a good rigorous analog because we don't have a notion of phase space. Yeah. Very good question.
Hi, thanks for the nice review so far. I would want to ask if there are any known connections between the Riemann hypothesis or the generalized Riemann hypothesis and the random matrix universality you presented.
Where the question from?
Oh, here.
Okay, yeah.
So the reason is, in the context of the generalized Riemann hypothesis, the distribution of zeros of very large imaginary part follows precisely the Gaussian ensemble that you mentioned plays a role in the random matrix universality. So I wonder if there could be a phrasing of the validity, whether it's true or false, in the language of gravity, or if there are any such speculations.
Yeah. So the zeros of the Riemann zeta function is a classical example in the study of classical chaos. I will say that it can be thought of toy examples. Toy examples for the general phenomenon of random matrix universality.
Is there such a thing as the square root cancellation for these cases you studied, where you have this weird cancellation between the square roots of the large imaginary part eigenvalues? Does this play a role?
Cancellation with square roots?
So the asymptotic behavior of the zeros are controlled by some special cancellations between the square roots of the eigenvalues. Is there such a thing in the gravity side? I just wonder if there is a rephrasing of the conjecture in terms of gravity.
I'm not sure what square roots you are talking about. Yeah, we can talk.
Andy. Yes, when you say that there are firewalls for some observers, do you mean literally that if you jump in the black hole the wrong way, you'll get burned up?
Okay, very good. It means, so the notion of firewall literally means it will burn up. So that's what I would call, define firewall. But the subtle question is about how to define the observer who jump into the black hole. So on the presence of a wormhole, apparently there are many gauge invariant definition of bulk observers. And it's an open question which bulk observers describe the experience of an infalling observer. So if you have a geometry without any non-trivial topology, then there's no issue of identifying infaller with a bulk observer. But if we have a geometry with a non-trivial topology, there are many possible Lorentzian sheets where you can define a bulk observer. And there are definitions that is gauge invariant under the diffeomorphisms. But there are many such definitions. What is not clear that I will come at the end is whether there's whether one can determine which bulk observer a infalling from a boundary infaller maps to on this complicated geometry. That is saying it's not clear that a CFT state uniquely determines the infalling observer experience.
Okay, so let's Genbing
Okay.
keep going with the puzzles.
I will talk about two puzzles associated to wormhole. First is the so-called factorization puzzle. We've seen in the wormhole contribute to the give you a kinetic contribution to product of boundary observables, and that's very natural in the language of an ensemble average, where you're thinking about wormhole is calculating ensemble average theory. Here, alpha will represent the parameter of the ensemble average, and P alpha defines the probability distribution. And in such cases, in cases like two lower dimensional gravity, such as J-cube Ted-bound gravity, this is literally true. We have a definition, non-perturbed definition of JT gravity, including the contribution from wormhole, and that is due to a matrix integral. And the matrix integral can be understood as an ensemble average of boundary theory. But how do we understand the wormholes if we have a holographic view of a single microscopic theory, namely a theory without ensemble average? We don't know. I think it's still a fascinating open question. But there have been proposals to understand it. One proposal is based on the periodic orbit picture in semi-classical chaos. There you can understand the contribution, you can rewrite the contribution to the spectral form factor as summation of pairs of closed orbits labeled by gamma and gamma prime. Then Michael Barry found that if you focus on a particular patterns in this summation, when the period orbits, the gamma and gamma prime becomes the same period orbits up to relative time shift, that leads to the same ramp growth in the spectral form factor. So in that context, if one just throw away the off-diagonal contribution, one again get this linear ramp inconsistent with the random matrix universality prediction. But it's a not computable approximation because this double sum is contain many more terms than the diagonal sum. Based on this picture, it is conjectured maybe for a single microscopic theory, one have both the wormhole contribution that represent the diagonal sum, but they also have some rapid oscillating half wormhole contributions. But it's not clear whether those half wormholes will have a geometric description. Another type of proposal to understand how wormhole can show up in the single microscopic theory is that because we are using gravity to calculate the observables, we will only get, we do an asymptotic expansion in the larger limit, we'll only get smooth results. And in the field theory, one can get smooth result by doing the so-called average over n or Largen filtering. One recent proposal is that if you have the so-called mailing average, when you have a quantity that depends on n, that you can do with the assumption that such an observable can be another continued in n and exhibit sufficiently rapid oscillations in n. Then one can do a mailing transformation of this function depend on n, and then and consider only the contributions of the poles from the mailing transform function. And that should give you a efficient way to do to give you a smooth, to pick up the smooth result in a single microscope theory with two strong assumptions on the behavior of this function. Another proposals in the community is that maybe one can instead do certain average of the possible sources. Let me make a small digression before going to the second puzzle. Because here I think there's a nice point as a comparison between random matrix universality, the concept of random matrix universality, with the concept of random matrix duality. Random matrix universality is a generic expectation that should apply to any chaotic systems. That means for certain chaotic theories, at certain time scale, the dynamics should just controlled by random matrix theory, regardless of whether the theory contains ensemble or not. And the method to trust this random matrix universality in the gravity is that we consider saddle point contributions, like what we did to construct this wormhole, which is a saddle point. It's a solution of Einstein equation, and we analyze its one-loop contributions. And sometimes maybe one need to generalize the saddle point analysis to consider nearly saddle point. And correspondingly, those, as we see in the first part, the wormholes will dominate or contribute only after a certain time scale that depends on non-trivially on the dynamics of the system. It depends on the polynomial frequency and the scrambling time. So those are system-dependent non-trivial data. On the other hand, it also makes sense to define an ensemble theories of random matrices. And there are systems, gravitational systems, that are literally due to an ensemble of random matrices. For those systems, theory is exhibit random matrix behavior at order 1 time scale. For such a duality, the definition of the measure is important, because you want to do an exact statement between the matrix integral and gravity calculation. You need to take in account of both the offshore and offshore contributions. And in the case of GT gravity, it's exactly due to matrix integral, and there are many fascinating generalizations of this duality. For example, general dilettante gravity, 2D minimal strings. I think we will hear some of the talk in this conference. And there are also proposals that pure 3D gravity can also be due to ensemble theory. Whether or not that is true is a fascinating open question. Now let's come to my last point of the talk I want to say. For that, let's go back to the theory with ensemble average. In a theory with ensemble average, because the measure is positive, is a positive thing, then that means the Euclidean gravitational path integral should automatically satisfy refraction positivity. For example, if we have a here, if you Z as denoting the insertion of asymptotic boundaries, then this object with a bunch of Z inserting on the top and the Z inserting on the bottom should satisfy refraction positivity. It's a positive semi-definite thing. Then we can define a Hilbert space by quotienting, review it as an inner product, and by quotienting the null state and complete it, we will define a baby universe Hilbert space, first recently discussed by Maxfield. That uses ensemble to define the baby universe Hilbert space, but it's not clear how bulk operators act on this Maxfield Hilbert space, and it's also not clear what's the connection of this baby universe Hilbert space with our more traditional defined canonical quantization Hilbert space in grafting. These two questions related to Maxfield in the context of a GAT grafting is analyzed by Pennington-Witten. In GAT grafting, you can construct both. It's an ensemble theory, so you can construct the Maxfield Hilbert space, but you can also construct the canonical quantized Hilbert space. And Pennington-Witten there exists an isometry map from the Maxfield Hilbert space into the canonical quantized Hilbert space. So the simple example is just to consider the case with closed universes. Here, it's a 2D grafting, so the spatial size, you can choose a spatial size as a geodesics. And the canonical quantized Hilbert space will be given by spans of the states associated with the closed geodesics. Those are labeled by the geodesic lenses of the closed circle S1. And the canonical quantized space will be a direct sum of the tensor product of many baby universe, many closed geodesics. Then one can define an isometry map from the Maxfield Hilbert space, which is labeled by the insertion of asymptotic boundaries into the canonical quantized Hilbert space by integrating over all Euclidean manifold, conditioning that the box size is a minimum cut among the Euclidean geometry. Namely, no matter how you cut it, how you separate this Euclidean path integral, the sum of the lenses has to be larger than the sum of the geodesic lenses in your future boundary. So that defines the isometry map, means it preserves the inner product. And because the canonical quantized Hilbert space have a non-commutative Bloch algebra, this defines a non-commutative Bloch algebra acting on the min cut size. I define those sizes as min cut. And because it's non-commutative, a natural consequence is that those Bloch operators are not diagonal in alpha sectors. And there are evidence this isometry could be an isomorphism. But there's also not very satisfactory point of this min cut map. First of all, there's no simple generalization away from ADS-GAT graph. And the operators does not have a simple limit in a fixed alpha sector, which we think we should understood if we finally want to understand a theory with a single microscopic view. So how do we understand the baby universe Hilbert space without ensemble average? In the previous two slides, we see that in the GAT graph-T, the Maxfield baby universe Hilbert space, presumably it's isomorphic to the canonical quantized Hilbert space, are closely connected to the existence of ensemble parameters. But if we don't have any ensemble average, those Hilbert space just becomes one dimension. So does baby universe have a one-dimensional Hilbert space? One way to understand, one proposal to understand this baby universe Hilbert space from the Lagrangian perspective is that one can maybe, when we look at the Lagrangian expansion, there's an emerging notion of ensemble. And to see the baby universe Hilbert space, let's consider entangled with the closed universe with the bath, and consider the algebras, operators acting on the best, which in the larger limit will becomes mixed, and then define the commutant of this larger algebra as the baby algebras acting on the baby universe Hilbert space. But how should we understand this closed universes at finite n where we do not take any larger limit? And one proposal is that maybe closed universes are unstable at finite n, so one cannot define it. Maybe there's another proposals where instead of large average of n, but average of sources that give you effectively some average over closed universes. There are also other proposals that maybe the claim that the property that there's a one-dimensional Hilbert space simply means the Bok observations cannot be described by the boundary state. The boundary state is one dimension. It cannot possibly capture the information about Bok. Similar as phenomena in the firewall case, maybe when you have a many baby universe, when you have a non-trivial topology, the Bok experience is not uniquely defined by the boundary state. To understand this Bok Hilbert space, maybe one need to condition on the existence of Bok observers and describe what the Hilbert space associated with such a new ingredient. And one have a new Hilbert space, not a CFT Hilbert space or ensemble Hilbert space, but a new Hilbert space associated with this Bok observers. I think at the current status, we don't have a conclusive answer about origin of a baby universe Hilbert space. Those are fascinating proposals, and maybe there are more proposals. Help us understand better the baby universe. That's all I want to say. Thank you.
Question.
Hi, Zhenbing. I have two questions. One is that in your earlier review of this ETH wormhole, so it's a double cone-like construction, and but I thought in JT there's also a double trumpet-like construction, but that's for Euclidean separation. And I just wonder if these two are connected.
Yeah, thanks for the question, and I'm very happy you asked it. So in the Euclidean, in JT graph, it's due to a matrix ensemble. So you can construct these correlations at any time scale. It's just because of the matrix. And you don't have matter. But the question, so that you can define it. The question is whether for those geometry can be generalizable to high dimensional situations, more realistic models. So that may be true or may not be true. So this ETH wormhole I'm constructed is a more universal generalization of these operators on the double trumpet.
Okay, so what I really wanted to ask is that in higher dimensional models, there's no longer known ensembles.
Yes.
And you showed that the existence of such geometry. Can you comment on, let's say, the origin of this?
Yeah, the orange is the similar origin as how double cone show up in high dimensional case. It show up because we believe the system should exhibit random matrix universality. So at a certain time scale, we expect this quantity should be controlled by random matrix dynamics. It's not saying that the system is due to a matrix integral or random matrix have an ensemble. It just means random matrix is such a quantum chaos is such a powerful concept that if the correlations are for correlations that separate at a long time scale, those should all be described by random matrix prediction. I don't want to average anything.
More questions? In the first half of your talk, thank you for the beautiful talk. In
Thank
the
you.
first half, the double cone wormholes, did they obey the Einstein equation at the apex? And if not, how are we supposed to do it?
Yeah, so the modification from the boost to the modified boost operator go around the this horizon, and it's a solution, smooth solution of Einstein equation everywhere.
Yes, as well. Okay.
Thank you for the beautiful talk. I have a question about your the first puzzle you talked about. So I think there's probably another proposal that is that there is a covering Hilbert space or operator algebra, and say the vector space itself is independent of n, but the norm depends on n analytically or meromorphically, and a certain integer value of n at a finite n, and then there are null states. And after you push in out the null state, you get the finite n Hilbert space. And then the gravitational theory computes are the quantities in this covering theory. Do you have comments on this proposal?
I think that's a very fascinating idea of a way it may be possible to generalize the theory away from integer n. So I think currently we don't have a very good theory for how to continuously define SUN as a non-integer value of n. So the quotient of the started with a Hilbert space at infinite n, and then quotient background with deep rings, etc. That looks like a promising direction to define the theory at non-integer value of n, but I think not explicitly have been. I would like to see how explicitly that calculation can be done. That first, and how this erratic oscillation piece can show up in that construction. That is not clear. So, namely, it's not clear that proposal can give you those half wormholes.
Maybe one last question. Yeah. Yeah. Wait a second. The microphone is arriving.
How wormhole can be create the firewall, how wormhole can create the firewall.
Okay.
Yeah.
The question is how wormhole can create a firewall. So so if we consider the sum of your double state, and we do a perturbation from the left black hole, and we jump in from the right, there are two phenomena that can happen. One is that this left perturbation is inserted at very late time. Then this enfolder will not see the left perturbation. But if the early of the left perturbation is sending very early, so remember it will trigger this shockwave geometry. That will cause any observer that falling from t equal to 0 to hit the singularity at Planckian time, close to the horizon. I think, yeah, maybe let me go Here, right. So here you can think about this Brook curve at the perturbation that sent in the early time, and then we have right observer who falling in. Then because of this null shift, this proper time goes to the singularity is close to 0. Okay, so that's a scenario where the observer who jumps in literally dies at the horizon. Okay, now if we so right now I haven't talked about the wormhole yet. But how a wormhole can create a firewall is through this following mechanism. Let's consider a state where this particle is inserted at very late on the left. So naively, it looks like smooth. This excitation happens very late, very far to the left, and the enfolder should not receive any inference from the left perturbation. So those are, I would call, smooth states. The observer survives at order 1 time after passing the horizon. But then it can happen that this geometry emits a baby universe, and the effect of the emission of the baby universe is that it shortens the wormhole length and brings the late perturbations very far back into the past. And then for certain bulk observers, this bulk observer will see these late perturbations sitting on top of the horizon. And that gives you a non-perturbative projection to the enfolding experience.
Okay, one last piece of wisdom by Daniel, and then we go for lunch.
Yeah, hi Janbi, thanks for the talk. I just wanted to comment that you had 2 problems at the end, but I think they're really just one problem. And the baby universe is a sort of more pure expression of the problem, because in the black hole case, the non-factorization is exponentially small. So we think it could have to do with some imprecision of the path integral. But in the closed universe case, it's leading order 1 non-factorization. And so maybe that's the best place to study the problem.
Yeah, these 2 puzzles are closely connected. It's true that if you have some like a leading contribution, this wormhole is exponentially small contribution. But if you look at quantity that like the leading contributor decays, then the wormhole also becomes dominates, regardless whether it's exponentially small or otherwise. Yes, so depends on whether you're willing for how patient you are about the time. But I'm sympathetic to you that these 2 problems are closely related, and maybe resolution for one can show hint on the second. Yeah, but also I think like just trying to define, trying to figure out this contribution for wormhole by taking average over the disconnected geometries. That yeah, that certainly looks like a nice thing to have. But thank you for the comment.
Daniel says we should go to lunch. I agree. So let's thank Janbin again.
Thank you.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, The event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, well, we're happy to start this session with Professor Juan Maldacena from the Institute for Advanced Study in Princeton, and he'll be telling us about wormholes in the imaginary distance mountain. Thank you, Juan.
Okay, thank you. Thank you for the invitation to give a talk. Thanks for organizing the conference. When I was a little kid in Argentina, people said that if you dig a hole deep enough, you can get all the way to China. So I'm here now. I wonder whether Chinese kids also say that if you dig a hole, you get all the way to Argentina. Today we are going to be talking about also holes in space-time. So this is work that, based on these two papers, one by Alex, Brian, and myself, and then the other by these four people. I believe Cynthia is here in the audience, so you can ask her more about the details of her paper. Okay. Now, space-time wormholes have been the subject of many recent investigations, and we will discuss here one of the simplest wormholes. These are the wormholes based on massless scalar fields. And we'll propose a certain interpretation, or you could say application, for these wormholes. And the idea is that wormholes set an upper bound for the continuation of couplings. So there is a certain analytic continuation of couplings that we could in principle do. By couplings in a theory of gravity, we mean vacuum expectation values of scalar fields. And there is a certain limit for what we can do. And we'll be more precise later. So, and I will skip the motivation and discuss a bit more motivation at the very end of the talk. And for now, let me just say that the outline is the following. So first, we'll start reviewing some wormhole solutions that are based on, then we'll discuss the boundary imaginary couplings, and then we'll discuss various examples of wormholes that use Kaluza-Klein reduction. And then we'll analyze a certain confusing wormhole that was proposed in string theory before. And as I promised, we'll end with a motivation. Okay, so let's first review the wormholes we will be talking about. So we'll start with the flat space wormholes. Before talking about the wormhole solutions, let's discuss the gravity action. So we're going to consider a theory of Einstein gravity plus, let's say, a scalar field. And or we could have several scalar fields with a moduli space. We'll always be talking about massless scalars. And notice these are standard Euclidean actions with right sign scalar fields. We normalize the scalars also. We pulled out the factor of G Newton in front of the scalar. That means these scalars are all dimensionless and they have a particular normalization. And so we'll later talk about distances in moduli space, and we'll mean distances with respect to this metric where we normalized it in this particular way. So that in the usual normalization means that what we are calling here phi is the field divided by some suitable power of m Planck. So the field in Planck units. Very good. Now, some of the scalars might be periodic, let's say axions, for example. But this will not be important for us. So the fact that the field will be periodic or not will not be particularly important for what we are saying. And whether we have an axion or not, we have always here the right sign for Euclidean action for a scalar field. Now, the basic solution is the following. So we have, this is a solution found by Gibbs and Strominger. We just have two asymptotically flat spacetimes, and they are joined by a wormhole. And the scalar field is imaginary in this solution. So in principle, the path integral for the scalar field is over real values of the scalar, but it so happens that for this solution, we have an imaginary field. So saddle point occurs for an imaginary field. And the asymptotic values of the field can be chosen. We are going to choose them in a symmetric way. Of course, we could shift these values by the shift symmetry of this simple axion Lagrangian. And we're going to fix them in such a way that they are symmetric and they acquire a particular value at infinity that is independent of the size of the wormhole. Okay. Now here is just the explicit formula that says in mathematics what I just said in words. And here we wrote here an additional formula, which is that the total difference between the two sides of the wormhole is this particular value independent of the wormhole size and depends only on the dimension. So the precise formula is not important, but well, will be important for some details, but I want to emphasize that it's independent of the size of the wormhole. And, very good. Now, let's discuss a little bit the case with many scalar fields. So if you have many scalar fields, then what you find is that the fields should move along a geodesic in the moduli space. This is particularly clear if you did a if you did a reduction to the radial direction of the wormhole. So that's basically more or less standard classical mechanics problem, and so the field should be moving along a geodesic. And so that's the only new feature, is that you had to find the geodesic, and then the solution is identically the same as the previous one once you express it in terms of the proper distance along this geodesic. And in particular, the proper length of the geodesic should be imaginary. Okay, so we are not moving in a real slice in the moduli space, but we are moving along an imaginary direction in the moduli space. I should emphasize that we don't require any symmetry on this moduli space. We could be a very general moduli space, so we could be moving along any direction. Okay. And sometimes if the moduli space has certain symmetries, then you can think of it as a time-like direction in the moduli space. There might be a continuation in the moduli space where you can view it as a time-like direction, but this is not a requirement for this discussion. Okay, that's already said. Now, let's discuss some features of these solutions. These are just solutions of the equations, and now we'll view them as solutions of a problem where we fix the asymptotic values of the scalar field on the two sides, on the two spacetimes. So we'll fix those values, and then we'll ask whether we do or do not find the solution. So this is what we could call the Dirichlet problem, where we fix the values of the scalar field. And what we find here is that the solution only exists for a specific value of the scalars, but not if you change a fixed value for the asymptotic value of the scalar field, and if you fix that boundary condition a little bit, then you don't find the solution. Okay. And once you fit it to that particular value, the size could be anything, as we said. And we have zero classical action, and of course this essentially follows from so all these features follow from a rescaling similarity of the action. So the action together with the scalar field, the Einstein action with the scalar field, can be under rescaling rescales by an overall factor. So that implies that if you have the equations of motion are invariant under rescalings. Okay. Now, for axions, sometimes it's common to consider the problem where the charge is fixed. Even for non-periodic scalars, we could consider the problem where the charge is fixed. By charge, we mean the momentum conjugate to the shift symmetry of this field, if we have a shift symmetry. And in that case, one finds that the action is actually proportional to this charge. And then we can view this Dirichlet problem as with arbitrary boundary conditions as really summing over all the wormholes with particular charges. I said previously that the action vanishes when we had Dirichlet boundary conditions, when we have this more Neumann boundary conditions, the action is actually proportional to the charge. And so when we consider the sum over all possible wormholes, we find a term, well, a term like this. So chi infinity is the particular value that we had before, and alpha is the Dirichlet boundary condition that we put for the scalar field. And what we see is that if, well, first of all, the sum diverges when alpha is bigger than this chi infinity and converges otherwise. And even if we wanted to find the saddle point of this action, just to go to the Dirichlet problem, we would only find the solution if this prefactor is 0. And when we find that, we don't find one solution, but we find an infinite number of solutions. So this is another way of saying this, seeing the same features. Very good. So there is, in this discussion, there is a prefactor here that depends on the details. It depends on the one loop factor, and that depends on the, well, on the details of the theory. But the question of whether this diverges or not is determined by large Q, and that's for large Q, the wormhole is very large, so that criterion does not depend on the details of the one loop factor and whether the theory has higher derivative corrections and so on. Okay, let's say this sort of once more. So if you are fixing the asymptotic value of the scalar field, that's what we call alpha in the previous transparency, then you find that for some range of values of alpha, the wormhole does not exist and this whole sum diverges. And then for values smaller than this, the sum converges, but and there is no wormhole solution, and only the wormhole solution Dirichlet boundary values exist only at this point. Now, similar solutions exist for ADS space, but in this case, the equations are no longer scale invariant, and the wormholes will have a size that will depend on the boundary conditions. And I won't present the formulas, I'll just give you a little graph here of what happens. Again, there is a region where the sum, there is a region where the sum diverges, and but there is a whole region where the wormholes can exist. So when they exist here, they exist as saddle points in that sum. They're related to saddle points in that sum, but the final sum will diverge anyway. And then there is a region where the sum converges. So chi infinity was that this was the value in flat space that's related to very small size wormhole, and this corresponds to very large wormholes in ADS space. Okay, so here in ADS there is a lower bound, for the conversions of these sums, which is smaller than what it was for flat space. So we see that the asymptotic boundary conditions might lie within a specific range in order for wormholes to exist. And as is standard, we can view the asymptotic value of the field as coupling constants for the gravity theory. This is true both in ADS or flat space. And so we are setting the imaginary, so what we are doing here is we are setting imaginary values for some couplings, and the theory might or might not be well defined for this imaginary value. By well defined, of course, the theory will not be unitary and so on when you continue to Lorentzian signature, but by well defined, we mean some theory that in Euclidean space is reasonably defined. Okay. Now we can imagine that we take a field theory and we analytically continue in the couplings, and as we continue in the couplings, it might be well defined for some time, and then we can reach a value where the wormhole exists. And the idea is that at this point, that Euclidean theory will not be even approximately well defined. Okay, there will be some trouble with this Euclidean theory. And we've seen that there is a trouble, which is that the sum over wormhole diverges, but we think that there should be some trouble even in a more native feature of the theory, in the sense that there should be some instanton which is becoming, instanton sum that is becoming large, even if we had the theory with only one boundary. Okay, so then this leads us to propose this bound, which is to say that if in flat space, if we are in d dimensions, we cannot displace a massless field an imaginary distance greater than this. This was precisely the value that we had for the wormhole in flat space, and that's the bound. And this, as we'll see, is very closely connected to the weak gravity conjecture. And there is a similar bound in ADS, so the detailed expression in terms of this a little smaller, so this distance is a little smaller than that one. Okay, so now we said that this is a bound, so the theory should become ill-defined here, but it might become ill-defined either before that point. So in other words, if as we are changing the asymptotic value of the scalar field or the coupling constant of the theory, then the theory might be more or less okay for some reason. And at some point, the theory in a specific UV completion, for example, a full string theory, it will cease to be well defined at this value. And the wormhole value could be this other one that is a little bit further. In other words, the theory could become ill-defined before you get to the wormhole bound. Okay, so this is just an upper bound. It doesn't mean that this is where the theory becomes it just should become ill-defined before that. Okay. Very good. So this was very generic. So now let's give some examples. Let's first start by giving an example of a theory that breaks down for imaginary values of the couplings. So let's start, for example, with n equal to 4 super Young-Mills theory that will be related to ADS5 times S5. So this discussion is somehow common to both cases. So there we have two scalar fields, phi and the Ramon-Ramon scalar field, or G Young-Mills and theta are the couplings of the Young-Mills theory. So these couplings could be real or complex, and we are going to be interested in making them complex. In the gravity theory, we have this term in the effective action, which looks like a hyperbolic space with unit radius. Okay, so in our normalizations we have unit radius, and so for an ADS5 wormhole, the half distance, so this limit is this particular value, and the only thing that will be relevant for what I'm going to say in a second is that this number is bigger than 1. So let's first set theta equal to 0, and then start continuing in phi. So if we start continuing in phi by an imaginary amount, we see that we'll get into trouble when the real part here of this quantity will become negative. There, just the action, for example, of the Young-Mills theory will not be bounded below. And this happens at this value, which is before the wormhole bound. So here we are using that this number is bigger than 1. Now something similar happens when we, let's say, keep phi real and change the value of theta or C0. And in that case, we run into trouble with instantons. So the instanton factor, the typical instanton factor is this. So this is normally a phase if theta is real, but if theta is imaginary, it can be a factor which is bigger than 0. And at some point, it can overwhelm this factor. And when that happens, sum over instantons could start diversion. And indeed, so using supersymmetry, Buff and Witten computed the partition function for a twisted version of this theory for n equal to 4 super Young-Mills. And the partition functions are given in terms of a function which indeed diverges when becomes singular, precisely at this point when theta reaches that particular value. Okay, so this is an example of what can go wrong in a theory where we analytically continue to imaginary values in the coupling. So this is not using wormholes of any kind. This is just an ordinary field theory computation. Okay, similar factors appear in the bulk. So if we think about bulk, the instantons, we see that the gravity correction will have, so Green and Gurpel computed this correction, this R to the 4th correction, and this coefficient will diverge when you get to this particular value of theta that we were discussing previously. And so in this case, we see that at that value, both the boundary and the bulk becomes become problematic. And in this case, both of those things were happening before we got to the imaginary values where the wormhole appears. So it's consistent with the idea that the wormhole is an upper bound, but well, something can happen before that. Okay, so so now let's discuss a wormhole example. So we'll start. The purpose of this is to connect to some other ideas that have been discussed in this similar context. Okay, so we'll start with the theory in d plus 1 dimensions and reduce on a circle. And yeah, so this is just a standard Kaluza-Klein reduction. We get this action. In this case, one point is that this scalar is not compact, it's not an axion, but we can still consider wormholes. We get new imaginary, and we get a wormhole. So that's the general case of the wormholes we have already found. And it turns out that in this case, the wormhole is just simply the Schwarzschild wormhole in 1 dimension more, right, in the higher dimensions. And so it's the same as the SSS wormhole that Shenbin was reviewing. And with a slightly different contour, I won't discuss these details. But part of the point of discussing this example is to emphasize the point that when we are looking at this imaginary value of the scalar, it corresponds to making the radius of the circle imaginary, and that corresponds to making a complex deformation of the internal manifold, which is a circle in this case. And the idea that nu equal to the imaginary distance bound is this particular value in this case, and it leads to a complex metric, which at that point violates the KSW criterion. So in this particular case, the imaginary distance bound is the same as violating the KSW criterion, because in this case, the wormholes were arising simply from this Kaluza-Klein reduction. Now, in fact, this is true for purely toroidal compactifications, let's say in higher dimensions, in geometric moduli, that the internal manifold, so KSW in the internal manifold is equal to the imaginary distance bound. So you can view the imaginary distance bound as a generalization of the KSW criterion to more general moduli, which might not be geometric. Okay, so it's simple general. So I've mentioned this whole thing just to explain why it's a generalization of that KSW criterion. Okay, now we'll turn to a second example, and we simply have the same setup as before, but we add the Maxwell field. And so in this case, again, you have a moduli space which after noticing that after making the Wilson line imaginary, becomes ADS2, and the trajectory of the wormhole could be some sort of Lorentzian trajectory in this ADS2. So what was imaginary in the Euclidean one now became. And well, in this case, we have a geometry related to the charged black hole, and it's actually ADS2 times S1, SD minus 1, that's the geometry. And if we added another field, then we could make the wormhole really asymptotically flat as opposed to asymptotically ADS. And the geometry we get is closely related to an extremal black hole. In fact, it's an two extremal black holes joined by a wormhole through the interior. Okay, so I think I'm running out of time, so I'm going to. I'm surprised that I ran out of time so quickly, I think. Okay, so these corrections that we're talking about, so we said we have a massless field, but the theory could have corrections of this form that involve exponentials of the massless field. And the idea is that the idea is that the imaginary distance bound arises. We think that the microscopic mechanism for the imaginary distance bound is that these corrections are going to become large when we set this imaginary value of the field. So for real fields, these corrections are very small. For real fields, these corrections are very small, but for imaginary fields, they can become very large. And the idea is that they will have to become very large at the imaginary distance bound or before the imaginary distance bound. Okay, so let me jump. I don't know what happened with time. I think I was cheated here. Okay, so let me discuss now one point, which are some string theory wormholes that were considered by Arkani, Hamed, or Geran Polchinski. So they consider a T4 compactification from 10 to 6 dimensions, and then they constructed some wormholes. And These are puzzling because these are wormholes in a string theory, so how in a microscopically well-defined theory, where we're not doing any averaging of any obvious kind. And what we'll see in this case is that actually, well, there are some details of what the wormhole is. I ran out of time, sorry to explain this. I don't know what happened here. Okay. So there is the wormhole trajectory that is embedded in some ADS2 space. And it turns out that there are some massless or zero action instants, some massless states or zero action states that appear through the wormhole trajectory. So, so in this case, again, it's a situation where there is some effect, which are these green things, which appear before you get to this imaginary distance bound. So the imaginary distance bound would be whatever the values, asymptotic values that they found in their story. And here you get some effect before that also make this wormhole invalid because the fields are moving over a distance which is bigger than the distance at which some large corrections appear. Okay, okay, so we cannot trust this, so that's the idea. And one reason to discuss this example is that the logic that they use to construct the wormholes, which I didn't explain, is the following logic, that maybe for one scalar, you have some displacement that might be too large and larger than you might expect. But if you have many, many scalars, you could have a wormhole or a situation where each scalar moves just a little amount. And that was used for the case of inflation. But we see that in this particular case, even though each scalar moved by a relatively smaller amount, you still have some problem with. And it would be interesting to see whether this continues to hold in some more sophisticated cases. Let's say a Calabi-Yau compactification with hundreds of moduli. Okay, yeah, that's what I just said. So in conclusions, the wormholes motivated this imaginary distance bound. And this is a bound, so at any point on the real slice, it bounds how much you can go along some imaginary direction. And we show examples where the bound is saturated, such as in the case of the SSS wormhole. And we also showed examples where the theory becomes ill-defined before we get to the wormhole bound. And you can say that this is a form of the weak gravity statement for scalar fields. Now, this whole discussion does not preclude, of course, other interpretations of the same wormhole. And I should emphasize that associated to these wormholes, there is always a closed Lorentzian universe. And this closed Lorentzian universe is always well-defined and fine, and it involves real scalar fields. So this Lorentzian universe is perfectly fine. But just the fact that if you are planning on defining the physics in this Lorentzian universe by considering this Euclidean solution, well, this Euclidean solution is on the verge of becoming ill-defined, so you have to be careful. Now I'll end up, I'm going to, I think, go over time to explain the motivation. And the inflation involves almost massless scalar fields, and we could wonder whether quantum gravity puts some limits on the range. And some issues about limits on range of fields were discussed by Oguri and Baffa. And here we proposed a limitation on the range, but in the imaginary direction. So it's not really a real bound. I would have been much happier with a real limitation of the range, but what we could do is an imaginary limitation on the range. So the question, now, of course, in certain supersymmetric theories, we do know that there is no issue with the range of fields, but you could wonder maybe the story is different in the sitter, that there might be a limit. And so just to explain, so if there was a limitation, imagine there was for some reason a limitation in the range of the field in the sitter. And also, let's incorrectly assume that it is the same as what we got for the imaginary direction. So in this case, then it would imply a constraint on the tensor to scalar ratio. And I think this should, yeah, if that range existed, it would be a factor of 3 smaller than the recent observational bound. This is just trying to put in context what these numbers that I mentioned mean. It would mean if the bound was real as opposed to imaginary. Unfortunately, for the time being, we have to be happy with the imaginary distance bound. So anyway, so if we found some real bound as opposed to what we found here, so that then it would be an opportunity to make a falsifiable prediction, and we should make it before the experimentalists rule it out. So this is just an advertisement for you to try to think about this type of problem. Okay, thank you.
Let's take time for one or maybe two quick questions. David?
A bound on so imaginary bound, I think, for a saddle point. Doesn't that just mean that you shouldn't allow that continuation? So what doesn't make any difference.
Well, I mean, are you thinking of, well, if you're thinking of the saddle point as the full flat space solution, yes, but normally we think of this flat space or ADS solution as a good saddle point to some problem with particular boundary conditions. And what we're doing is just changing the boundary conditions, right? And claiming that the theory with the boundary conditions that differ by this imaginary amount, it just ceases to be well defined. Now you might say this is, okay, well, you can have various reactions. Who cares about imaginary directions? And this is a very fair discussion, you could say as well. But well, it's something we can say at least. So we do what we can.
So one question here. So you talked about this bound on the imaginary coupling, I mean, coupling in the imaginary direction or the
yes,
in the direction of imaginary values of the scalar field. But if, let's say, there's some singularity or something that lets you see that there is a bound, but I mean, can we not go around it in the complexified plane, complexified space of the fields, or is there a natural boundary that surrounds?
Yes, yes. Yeah, there are two things you could say. One is you could perhaps go around. The other is that maybe so the logic about the bound was that there was a divergence in the sum. Yeah. But it's been proposed by Maroff and collaborators that maybe the wormhole never contributes to anything. So there are other ways of thinking about this problem, and so that's why we call it conjecture. So the gravitational path integral doesn't come with a contour, and different choices of contour might lead to different prescriptions. So here we assume that these solutions, let's say the solutions for fixed charge, would be showing up. And if you assume that, then now the question about analytic continuation. So the typical function that has a single, so there is a result in mathematics that if a function has some radius of convergence and it's a typical function, then you cannot analytically continue. So now the question is whether the functions that appear in string theory are typical functions or not.
In the Wafa-Witten partition function, for example, the entire circle is not allowed.
Yeah, so in the example that we saw of the n equal to 4 super Young Mills theory, that's an actual boundary, so you cannot continue beyond that.
Thank you.
Okay, in view of time, I think we should take any further questions in the break, and let's thank Professor Maldacena again. Okay, we're very happy to have Professor Tom Hartman from Stanford, and he's going to tell us about triangulating 3D gravity.
Okay, thank you very much. Thank you to our hosts and the organizers for the opportunity to speak. So there's a lot of evidence now for this coarse-grained or ensemble average version of the ADS-CFT correspondence, where higher topology spacetimes in gravity, in the gravitational path integral, calculate or encode the statistics of black hole microstates. Now on the left-hand side of this ensemble average version of the duality is general relativity plus corrections as calculated by the path integral. And so this can only fully make sense in low dimensions. If we're in 4 dimensions or higher, then general relativity is not normalizable, and we have to treat this as a low energy effective theory. We can still have random matrix universality, as Zhenbin reviewed earlier today, and this can make sense as a low energy approximation. But in low dimensions, at least in dimension 2, and possibly in 3D, there's a chance for a precise duality. In d equals 2, we have JT gravity famously dual to random matrix theory. In d equals 3, the story is still unfolding, so we don't know the full answer here. But there's a lot of evidence that pure 3D gravity, as defined by the gravitational path integral, is dual to a random 2D conformal field theory, or an ensemble average over 2D CFTs. Though we don't have a precise definition of this ensemble average in the way that we do for random matrix theory, but there are many things that we can say about the random CFT. So the data of an ordinary fixed CFT are the spectrum, rho, and the OP coefficients, the CIJKs, which are the matrix elements of the primary operators. So the observables of a random CFT are the statistics of that data, of the spectral data and the OP coefficients. Ideally, we'll find something like random matrix theory that computes all such statistics and agrees with the path integral of 3D gravity. So far, this has not been done, but we can calculate the statistics order by order, case by case, using the conformal bootstrap. And in many examples, the bootstrap results agree with the gravitational path integral in 3 dimensions. In this talk, I'm going to focus on the gravity path integral that calculates these OPE statistics and how to make sense of that path integral to learn more about the structure of the random CFT. So when you calculate these path integrals, the contributions come from Euclidean wormholes. The leading term is the 2-boundary wormhole of Maldacena and Maus. So this is a Euclidean solution in ADS3 that has 2 asymptotic boundaries. And there are 3 particles, in this case, going through the wormhole. So this has the boundary conditions with 1 copy of the 3-point function on the left and another copy of the 3-point function on the right. So this calculates for you the squared 3-point function, or the squared OPE coefficient, these CIJKs. And this produces, when you do the calculation, this produces Gaussian statistics that agree with the conformal bootstrap. This variance of the ensemble is a function of the conformal weights, which I'll parameterize by the Liouville convention, parameterized by P. And for the most part, I'll talk about pure gravity, where the only states in the theory besides the vacuum are black hole microstates, and so P is a real number, so that the states are above the black hole threshold. It's convenient to define normalized OP coefficients with unit variance, and I'll call that capital CIJK. So that was the Gaussian leading term. There are also non-Gaussian corrections, such as this 4-boundary wormhole. These more complicated wormholes, like this one pictured here, are usually calculated using Virasoro TQFT. So this is a topological theory related to SL2R Chern-Simons theory that provides some simple diagrammatic rules to calculate many of these wormhole amplitudes and makes it much easier than trying to use the metric formalism. So 3D gravity has 2 copies of SL2R, so you have gravity related to Virasoro TQFT squared. In the Virasoro TQFT approach, the way we phrase these wormhole calculations is in terms of networks of Wilson lines. So the Maldacena-Maus wormhole that I had on the previous slide becomes this theta graph. Each of the trivalent vertices in the graph corresponds to an ADS boundary. So the 2 vertices in this graph are the 2 ADS boundaries of the previous slide. And the Wilson lines are labeled by conformal weights. Those are the P1, P2, and P3. So we've normalized the variance to 1, so this theta graph gives 1 in the TQFT. The other most important Virasoro TQFT calculation that we'll need corresponds to this four-boundary wormhole, the non-Gaussian contribution. So in Virasoro TQFT, again, each of these boundaries becomes a trivalent vertex of these Wilson lines in the Chern-Simons formulation. And this particular wormhole becomes the tetrahedron graph. So we square that. If you calculate this in the TQFT, this gives a special function, which is the Virasoro 6J symbol. Virasoro 6J symbol ups normalization is the fusion kernel for the crossing of the four-point function on the sphere. So this is just a special function that's known. It's complicated, but it's a known function that will come back later. Now, in the rest of this talk, I'm going to describe a different approach, a complementary approach to the path integral, calculating this path integral of 3D gravity based on triangulations. Here's the basic idea. What we're interested in is calculating complicated higher topology, the path integral on some complicated higher topology wormhole saddles, like topologies like this one, not saddles. So this is an example where, say you want to calculate the average of the CFT partition function of genus 2 and the CFT partition function of genus 3. Then this is the kind of geometry that you have to sum over topologies, and this is a sort of typical example that you'll find. So there's a genus 2 boundary for one of the partition functions, a genus 3 boundary for the other one, and then there's some complicated topology inside the interior of the 3 manifold, and you need to calculate the path integral on this topology. Our strategy to do this will be first to split this geometry into the core and the asymptotic ends. So the core is the gray region in the center, and the asymptotic ends connect to the conformal boundaries. The second step is to decompose the core into what are called generalized tetrahedra, which I'll define in a minute. But these first two steps, splitting into the core and the asymptotic ends, and then decomposing the core into generalized tetrahedra, this follows the work of Thurston on hyperbolic 3 manifolds in the 70s and 80s. The last step is to do the path integral on the core. And what we'll show is that the exact path integral on the core is computed by a novel TQFT called the conformal Turayev-Viro theory, or CTV. So a generalized tetrahedron is a tetrahedron with truncated vertices. You cut them off by a finite amount. So this is an 8-sided polyhedron with 4 hexagonal faces and 4 triangular faces. On shell, this becomes a hyperbolic tetrahedron, but it's a hyperbolic tetrahedron with some of its vertices that you pull out beyond the conformal boundary of hyperbolic space. This makes sense. You can make precise sense of this by working in embedding space, and then you literally move those points outside past the conformal boundary in the embedding space. When you move them out past the boundary, these hyperideal vertices get truncated on geodesic surfaces. So the defining feature of this geometry is that the triangular faces are orthogonal to their neighbors. The core is then going to be constructed by gluing these generalized tetrahedra on some of their faces. This is AI's attempt at drawing what that would look like. You can't really draw this because these are not handle bodies. You have to imagine that you take a bunch of these generalized tetrahedra, you glue them together on some of their faces, and you get pictures like this, but with some additional gluings. And our goal now is to do the gravity path integral on such a manifold. So we're trying to define the gravity path integral on a compact region, and our first thing we need to do is to impose boundary conditions. The boundary conditions we're going to impose are the following. So first we choose a Pants decomposition of the boundary. These are the blue curves on the boundary of the core. Now we'll fix the lengths or the dihedral angles, the bending angles at those blue curves that will become geodesics. The gravity path integral with those boundary conditions, if we fix the lengths, I'll call that Z sub L. And if we fix the bending angles, I'll call that ZA for fixed angle. The boundaries that you get when you impose these boundary conditions are called pleated surfaces. These are these are surfaces whose intrinsic geometry is hyperbolic, like two-dimensional hyperbolic surfaces. They have vanishing extrinsic curvature, except on geodesics where they can bend into corners. And that's how a picture like this one, although I drew it as smooth, once you impose these boundary conditions and you solve the equations of motion, those blue curves turn into the corners on a picture like this one. So the fixed length path integral on this core, this is what's calculated by Virasoro TQFT. So the fixed length path integral is Virasoro TQFT squared. This is just restating the standard result on Virasoro TQFT, relating it to 3D gravity, but in the language of this compact region. The next step is to triangulate the core. Semi-classically, this can be done with fixed length boundary conditions. However, it turns out that we'll find a nicer exact answer by working at fixed angles. So we're going to fix now not the geodesic lengths of those blue curves, but the angles that they bend. And what we'll find is that the fixed angle path integral on the core is calculated by this other TQFT, the conformal to Raya-Viro theory. So this is the equation that we're after. It says that the fixed angle gravitational path integral is given by this topological theory, CTV. So now I'm going to explain what that theory is. So CTV is a topological theory that assigns amplitudes to trivalent graphs, like Virasoro TQFT. And I'm first going to describe it as a TQFT without any reference to gravity. Then we'll come back to gravity. The partition function of the theory is denoted this way. It depends on, so the data that you have to provide, you have to choose a closed three-manifold, that's ME, and then you put some trivalent graph gamma in that three-manifold with edges labeled by conformal weights, P. Now to calculate the partition function, choose a triangulation, T. Edges of T that belong to the graph are called external edges, and the other edges are called internal. Now to each tetrahedron in the triangulation, we assign a Virasoro 6J symbol. This is the same Virasoro 6J symbol that showed up before in the calculations of the Virasoro TQFT, with one important difference, which is that the rows have been swapped. This is not a symmetry of the 6J symbol. This corresponds to dualizing the tetrahedron. That is, replacing the vertices with the faces and the faces with the vertices. So this is a dual version of the 6J symbol. Now I can define the amplitude of CTV. So we have a Virasoro 6J symbol for each tetrahedron. We multiply those all together. And then integrate over the conformal weights on internal edges with the Cardy density of states, which I've called here rho 0. This formula is the natural generalization of the standard Raya-Viro theory to a non-rational CFT. So the standard theory is defined for compact gauge groups or rational CFTs. The formula is almost the same. However, there's an important difference, which is that in CTV, the total number of states is infinite. So this would be, in a rational theory, this would be the total quantum dimension. But in CTV, if we integrate the Cardy density of states, this is exponentially growing and we just get infinity. And this introduces some important differences, because if you look at the literature on Raya-Viro, there's these n's all over the place. So some of the results carry over to CTV and some of them do not. The most crucial difference is that this restricts to certain types of triangulations. So in a fully topological theory, you would have some amplitude that's completely independent of the triangulation. But because of this infinite number of states, what happens is that you can add edges to your triangulation, as in this picture here. You can add a new edge, and that doesn't change the answer for the amplitude. But you cannot add a new vertex like this one. So if you try to add a new vertex in an ordinary Raya-Viro theory, it doesn't change the answer. But if you try to do this in CTV, you introduce a divergence. From the point of view of TQFT, this is strange, but actually from the point of view of gravity, this is exactly what we'd expect, because when we get to gravity in a minute, adding a new vertex like this is like adding an additional ADS boundary. And we don't expect in gravity that you can add a new boundary in the middle somewhere and then integrate over it to get back the answer you started with. So here's an example. This is one of the simplest calculations you can do, this knotted graph. And we're going to view this as a graph in CTV as a graph that's embedded in the 3-sphere. So if you stare at this for a few minutes, you can convince yourself that this graph embedded in the 3-sphere can be triangulated with a single tetrahedron. You take this tetrahedron here, and you glue the 2 front faces together, and you glue the 2 back faces together. That makes a closed 3-manifold, and the edges combine into this graph structure. In this case, there are no internal edges. And so the amplitude is very simple. It's just the 6J symbol for that single tetrahedron. We don't have to do any integrals. So this is an example where this gives an example of a CTV calculation. And in general, these rules are very easy. If you have a decomposition of your manifold into triangulation, into tetrahedra, then you can easily write down the amplitude. Now I want to discuss the relationship between CTV and the Virasoro TQFT. So there's a well-known relationship between the standard Teraya-Viro and Chern-Simons theory for compact gauge groups, which says essentially that Teraya-Viro is Chern-Simons squared. So we anticipate something similar for our case, relating CTV to the Virasoro TQFT. It turns out that they're related by a modular S transform. So here's the precise equation. It says that, so on the left-hand side is the CTV amplitude, and it says that that's equal to the Virasoro TQFT amplitude squared, where you then do a modular S transform on every one of the Wilson lines. This modular S matrix S is just a cosine, so the transform is also just a Fourier transform when expressed in terms of the weights P. I'm not going to go through the proof, but the basic idea of the proof is that this modular S transform takes the triangulation, and in that triangulation, it replaces each tetrahedron by the dual spine of that tetrahedron, which is this little piece of a handle body that's drawn inside. So that dualizes all the edges and gives you a dual calculation of the same amplitude. An identity like this was already known in the compact case, the derivation in the non-compact case is similar, but you have to avoid these factors of infinity. So there are factors of infinity floating around, but it turns out that you can get rid of them, and you can show that the same identity holds in CTV. So now we can return to 3D gravity. First, I need to tell you what manifold gravity is defined on. So CTV and Virasoro TQFT, these were both defined for some graph in a closed 3-manifold, ME. In the correspondence to gravity, the gravitational theory lives on the complement of the thickened graph. Okay, so you take this graph, here's our example again. You take this graph, you fatten it out, and the complement is a manifold M, which is a compact manifold with boundary. And we're going to impose fixed length or fixed angle boundary conditions on the meridians of the graph. So the red curves on the boundary of M. Then you can find the geometry just by taking these same pictures we had in our triangulation and truncating the tetrahedron. So since we flattened out the graph, that chops off the vertices of the tetrahedron. And in this example of this knotted handcuff graph, the on-shell geometry on the complement is a single generalized hyperbolic tetrahedron with some of the faces glued together by the same gluing pattern that we had earlier in the TQFT calculation. So this gives you a way of translating CTV calculations into 3D gravity so far just of translating the manifold from CTV into gravity, and now we want to translate the amplitude. So now I can restate again this main result for the gravity partition function and its relation to the CTV amplitude. So we'll start from the fixed length path integral. That says that the fixed length path integral is Virasoro TQFT squared. And now we take the Fourier transform or the modular S transform of both sides of this equation. When you put all the i's in the right places, what that does on the left-hand side of the equation is it changes the fixed length boundary condition to the fixed angle boundary condition. So on the left-hand side, the Fourier transform takes us to fixed angle. On the right-hand side, we've shown a few minutes ago that Virasoro TQFT squared, if you do that, the Fourier transform gives you this Turayev-Viro theory. So we've derived this relation between the fixed angle path integral and CTV. That was the main identity that I wanted to get to, and explains how we can use this theory to calculate the path integral on the core. In the semi-classical limit, this gives you a nice decomposition into these generalized tetrahedra, so each tetrahedron contributes a factor related to its volume. So we've succeeded in writing the gravity path integral in terms of a triangulation, where you have one 6J symbol for each of these truncated tetrahedra. Recently, Jefferson Wang gave another interpretation of the right-hand side of this equation using the open, or BCFT, version of the 3D gravity Virasoro TQFT. This also connects today's talk to the work of Janet Hung and collaborators that was reported in the last strings meeting, which was also in BCFT. And putting it all together gives the following picture for 3D gravity on a compact hyperbolic 3-manifold. So I'm not going to give the derivation of these BCFT results. I just want to explain how what I've said today fits into the BCFT. So in a BCFT, there are two types of 3-point functions. There's the ordinary 3-point functionCijk, which is the one that we were talking about earlier. And this is the one that's calculated, that we usually discuss these statistics for in Virasoro TQFT. And then there are the 3-point functions of boundary operators, say on the boundary of the unit disk. So call these things Bijk, and those also have some statistics in this ensemble dual to 3D gravity. So the summary, putting these various papers together, is that with fixed angle boundary conditions, the path integral on the core, which is calculated by the Turayev-Viro type theory, calculates the statistics of the boundary operators, so the moments of these Bijks. With fixed length boundary conditions, the path integral on the core, which is calculated by the Virasoro TQFT, calculates the statistics of the ordinaryCijk OB coefficients. And the two are related by this modular S transformation. The fact that the boundary data and the bulk data are related by the modular S transformation is some non-trivial constraint on the type of boundary conditions in these theories. So let me wrap up by mentioning a couple of open questions, which I think are solvable in the near future, hopefully in the near future. So the first one is there a similar story with positive cosmological constants, so pure gravity in three-dimensional de Sitter space? The answer is that there probably is. So in fact, the history of this is a little bit the other way around. And the techniques that I've used in the talk today were actually borrowed from work that was originally done in de Sitter. So this really goes back to the work of Planzano and Regge, who gave a triangulation of, well, you can interpret their work as a triangulation of 3D gravity with zero cosmological constant. Then came along Turayev-Viro. They were writing down invariants of 3 manifolds. They weren't trying to study gravity, but it was soon recognized that the standard compact Turayev-Viro theory is a discretized model of quantum gravity in DS3. And this was studied extensively in the spin network literature, some of which I cited earlier in the talk for this identity of the S transform, and that was important here. And then today we talked about negative CC. So the methods are similar, but the crucial difference was this factor of n. Now, I don't exactly know how to put this all together and give this give the answer for pure gravity in DS3, but this suggests a statistical interpretation of pure gravity in de Sitter. The other open questions I'll just leave up here for you to read yourselves so that we have time for questions, and thank you for your attention.
Any questions? Andy?
Yeah, could you just say a few more words about the comparison to the bootstrap? Usually I think of the bootstrap as being in 1/3. How do you get the statistics of things in the
So
bootstrap?
the way these bootstrap calculations work is that you start with some input data from the gravity side. In this case, the input data is just the variance of the ensemble and the Cardy formula. And then you take that and you plug it into the bootstrap equations and demand that they hold on average. If you take that leading order data and you plug it into the bootstrap equations and demand that it holds on average, you get some equations for the average CFT data, and then you can iterate those equations to derive higher statistics.
I see. Thank you.
So, Tom, one question. So here you talked about how this you can glue the triangle, various tetrahedra together to get this, associate 6J symbol to each of them to get the partition function. But at least in the compact case, I know that this Thoraev-Virot theory, in addition to having 6J symbols associated with the tetrahedra, also has some factors associated to the edges and its local neighborhood, depending on how many tetrahedra are being glued at a given edge. So such factors are present here, and because I couldn't see them in the formulas.
Yeah, so I wrote the simplest case, which is for tensionless brain. So there's when we talk about the BCFT ensemble, we can assign tensions to the brains. I wrote the formulas for the simplest case where the brain tensions are all 0. That's the one that I think has the most direct relationship to the ordinary closed ensemble. But you can include brain tensions, and presumably that should be accounted for by those factors.
But so if you glue, I didn't quite get how many tetrahedra were glued around a particular edge. Depending on that number, you might be engineering some sort of a conical defect also. So is it that this triangulation will introduce these cone defects?
So this doesn't lead to any defects in the interior. So you glue together some subset of the faces. If you end up with an internal edge that's fully surrounded, then you integrate over it. So that after integrating over it, it becomes smooth.
Okay.
One question here, Nikita.
So you showed two types of boundary conditions, fixed lengths or fixed angles. So these look like two kinds of real polarization. Is there a formalism where you fix conformal structure on the boundary or conjugate conformal structure? That might be more natural from the statistics of CFTs.
Yeah, I think that boundary condition is the boundary condition that has the asymptotic ends put back in. So basically, when you do this decomposition into the core and the asymptotic ends, you should think of the core as being responsible for the statistics of the OPE coefficients, and then the asymptotic ends as being responsible for the conformal blocks. And the translation between those is like this change of basis that you're describing.
Yeah, one question over there.
Thank you for the presentation. I was wondering why you choose as a core element the triangulation and not higher order quartillation or five-vilation or whatever they call it. And if it is necessary to use triangulation, the mention that the generalized triangulation is an octahedron instead of a tetrahedron. Would that give you some more properties or interesting properties to study in your formulation?
So for the first question, why triangulations? The only answer I have is that because there's a nice way to calculate it using the Thoraev-Virot approach. So I think you could glue them into more complicated polyhedra, but then you could always decompose that into these truncated tetrahedra. So the second question was whether the 8 sides is important for something. Well, in this relationship to the BCFT, I think the answer is yes, because the way you should think about that relation is that those triangular faces become like the B's. And so each triangle is like one of the B's. And so if you calculate the statistics of 4 B's, those are the 4 triangles. And so they're important for that.
Okay, I think we can take one more quick
thank you.
question.
Thanks, Tom. I guess maybe a vague question, but many of the things here look like pretty close generalization of the 2D case. Like, for instance, you can think of the relation between CTB and BTQFT as gluing a trumpet or something. Do you see any evidence of some sort of analog of topological recursion, some recursive structure for these partition functions?
Good. Other than the fact that you can glue tetrahedra together, and this is how you glue them, I don't know of anything that looks like topological recursion. I think that there's a proposal in some of the work that's cited here that the full theory, you need to combine everything I've said here with topological recursion that calculates for you the spectral statistics. But that's the most direct thing I know of. I don't know how to really turn it into, I don't know how to reduce it to JT and turn it into that problem literally.
Okay, let's thank Professor Hartman again. And we now have a coffee break.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, so let's begin this session. We'd like to welcome Professor Matthew Hedrick from Brandeis University, and he's going to talk about holographic entropy, inequalities, and typical states.
Thank you. Thank you, Spenta. And I'd like to start by thanking the organizers for inviting me to speak at this very impressive conference. This is certainly the most opulent lecture hall I've ever given a talk in, probably ever will. Before I start, I'd like to give a shout out to my collaborators on most of the work I'll be talking about. So Veronica Hubany is a professor at UC Davis, probably known to many of you. Guglielmo Grimaldi is my PhD student, and he's done incredible work on almost all of the things I'll be talking about today, and he is going to be applying for postdocs this fall. So let's jump in. So this is a talk about the famous Ryutake Yanagi formula, which is a gift that Tadashi and Shinsei gave to us 20 years ago now, and which has taught us an enormous amount about entanglement entropies in holographic theories. Let's just recall what it's about, first of all. So first of all, the entanglement entropy given a bipartite system is defined by the von Neumann entropy, and in the particular, the von Neumann entropy of the reduced density matrix, which is obtained by tracing out the complement of your given subsystem A. In the case, for example, that your state is a state of a quantum field theory, then typically we would be talking about the state of the subsystem defined by a spatial region. So here, for example, my quantum field theory would be defined on a circle, and my spatial region would be A, this arc of a circle. Now, all of the pictures I'll draw in this talk are of one-dimensional quantum field theories and two-dimensional bulks. That's purely a limitation of my drawing abilities. Nothing I say will be dependent on the number of dimensions of space. It's very important for us to recall the regime of validity of this formula. So within ADS-CFT, this formula is valid under three conditions. The first is that we have to be at large n, which means that the bulk has to be well described by classical physics. The bulk also has to be well described by Einstein gravity. That means strong coupling on the boundary. And thirdly, we have to be in a static state. Static here means not stationary, not an eigenstate of the Hamiltonian, but rather an eigenstate of the time reversal operator T. In other words, we have to have a moment of time symmetry, and that also implies not only that the state is invariant under the time reversal symmetry, but that the region that we're talking about, the region A in this case, lives on that moment of time symmetry. The fact that we have a moment of time symmetry means we have a distinguished slice, distinguished Cauchy slice, and since the state is invariant under that time reflection symmetry, there's a distinguished bulk Cauchy slice, and that's what we're working on when we write down the Ryutake Yanagi formula. And here, so then we're looking for the minimal surface, which is homologous to the boundary region A, which means that there exists a bulk region on that Cauchy slice that interpolates between A and the surface. And I'll call the minimizing surface gamma sub A. So these are, I'm just emphasizing these, this regime validity of the formula. It's not a limitation on our knowledge. We know how to go beyond all of these three criteria, and I'll be talking about that in the talk. But at first, I just want to keep with this very simplest version of the formula. Now, of course, like ADS-CFT itself, the Ryutake Yanagi formula and its generalizations have taught us an enormous amount about both sides of the duality. So they've taught us a huge amount about quantum gravity from things that we know about entanglement entropies, and they've taught us a huge amount about the behavior, the properties of quantum field theories, of entanglement entropies in quantum field theories and many body systems, because it's very calculable. So one thing that people outside the field don't necessarily always appreciate is the extent to which RT gives us a view that we don't have otherwise onto the behavior of entanglement entropies in quantum field theories. And I don't just mean, usually, of course, holography is incredible for telling us about the behavior of strongly coupled large N quantum field theories. But in this case, it's not just that. Any quantum field theory, it's very, very hard to calculate the entanglement entropes in first principles from. And so, you know, the way I like to think of it is that the behavior of entanglement in quantum field theories is like a beautiful room, like this room, and we can only see that room by looking at it through a keyhole, and the keyhole is the Ryutake-Nagi formula. So by looking at it through the keyhole, we see that the room is very beautiful, but we can only see a little part of it, and we're kind of straining to see the rest of the room, okay? And what I hope to convince you of in this talk is that even though this is the very simplest version of holographic entanglement entropy formulas, it still has mysteries for us. It still has things to teach us about both directions, about quantum gravity and about quantum field theory. Okay, more specifically, what I'm going to be talking about are linear inequalities obeyed universally by entropies that you calculate by the Ryutake-Nagi formula, and I'll show you a few examples in a second, and I'll also explain why we're talking about linear inequalities. So the first and simplest example is called subadditivity, and I just want to walk through the proof. It's incredibly simple. It's hardly even worth writing down because it's almost obvious when you think about it. But the ingredients are the same ingredients that we're going to use to prove much more complicated inequalities. Okay, and the technique is always the same. You write down the minimal surfaces, the RT surfaces for the terms appearing on the left-hand side. In this case, we have the surface for A and the surface for B. And out of those, you construct candidate surfaces for the terms appearing on the right-hand side of the inequality. In this case, we only have one term that's S sub AB, so we need a candidate surface for AB. And a candidate surface for AB is gamma A union gamma B, because that is homologous to A union B. That's not to say that it is the RT surface, but it's a candidate surface, which I'll write as gamma tilde AB. Okay, and once you have and of course it has the same area as gamma A plus gamma B. And so then you're done proving the inequality. Now, by the same technique, we can prove more complicated inequalities, such as strong subadditivity. And here, the proof technique is exactly the same. But the only thing is you have to be just a tiny, tiny bit more clever in constructing those candidate surfaces for the right-hand side terms, that you construct them by cutting up the surfaces appearing on the left-hand side terms. And more precisely, what you do, because what we're really interested in are things that are in the appropriate homology classes, what you really do is you look at the union and intersection of the homology regions for A, B, and BC, and those give you the candidate homology regions. The union gives you the candidate homology region for ABC, the intersection for B. Okay, and you can keep playing this game and get more inequalities. So the next one, oh, sorry, there was one very important thing I wanted to emphasize. Which is that it's surprising how simple these proofs are, given how complicated the properties that they're proving are, and in particular the fact that I just want to emphasize the fact that there's almost no physics once you assume that you have that somebody gave the RT formula. After that, in proving the inequalities, there's no physics that enters. So I did not use any bulk equations of motion. I did not use any boundary conditions, any energy conditions, anything like that. So these inequalities are valid just based on the basic idea that we have some kind of Riemannian metric on a manifold with boundary, and then you're done. Okay, and that's going to be true for a little while in the talk until it's not true anymore. Okay, so, but anyway, let's go and look at more inequalities. So this one is proved the same way, and I'm not going to go through. It's just a more complicated picture. And this one is called MMI, which stands for superadditivity of mutual information. Because this one is starting to look a little complicated, to get the physical meaning of these inequalities, it's helpful to rewrite them in terms of the mutual information. And you see they're very simple. Subadditivity is just that the mutual information is non-negative. Strong subadditivity, that's monotone. When I add C to B, the mutual information with A cannot decrease, and then superadditivity of mutual information is superadditivity of mutual information. Okay. Okay. Now this cut and paste proof can be formalized into a combinatorial gadget and made more systematic, and you can do basically computer searches for it. So that was initiated in this paper a while ago. And one of the key steps is to turn the problem into a problem in graph theory. So you just think about all the RT surface. So I have a fixed geometry and I fixed a set of boundary regions, and I'm interested in finding inequalities for that set of boundary regions. So first I cut up the bulk along all of these RT surfaces. Those are codimension 1. They leave codimension 0 regions. I associated those to vertices of a graph and the pieces of the RT surfaces to edges, and I weight each edge according to its area divided by 4g Newton. And that gives me a weighted graph. And then on that weighted graph, by construction, the entropies are the min cuts on that weighted graph. And on the other hand, you can go the other way. If you give me a weighted graph, I can construct a bulk geometry whose RT entropies are the min cuts on that weighted graph. So in other words, you can go back and forth from geometries to graphs, and therefore you can reduce this problem, which a priori is a problem in Riemannian geometry. It's really not a problem in Riemannian geometry. It's really a problem in discrete math in graph theory. And from that, you can prove nice things, for example, that the inequalities are only linear. The fact that the inequalities are only linear and that there's a finite number of them for a fixed number of regions. So that leaves what's called the entropy cone, the holographic entropy cone, which is the set of entropy vectors that are allowed by all of the inequalities that are obeyed by the RT formula. The entropy cone lives in entropy space, which is the space of entropy vectors, and that's just where you take, for a fixed number n of regions, you look at the entropies of all the single and multiple parties, and that gives you a vector which is in a 2 to the n minus 1 dimensional space. -1 because we don't include the empty set, because the empty set always has entropy 0. So that leaves a 2 to the n minus 1 dimensional space, which is the space where the entropy cone lives. And by virtue of the fact that it's a problem in graph theory, you can prove that it's a convex polyhedral cone, which means you only have linear inequalities. Now, you might ask, so I emphasize that there was only one, that you always use this one proof method. Actually, there is another proof method which can be used to prove the 3 inequalities that I already showed you. And in fact, the last time I spoke at Strings, which was exactly 10 years ago in Beijing, I proved the first 2 using bit threads. And so you might ask whether maybe there are inequalities that you can prove using bit threads that you can't prove using cut and paste. So that was an open question in the field for a long time. And in fact, the answer is no. So you can prove a theorem that every true inequality obeyed by Ryutakanagi entropies can be proven by the cut and paste method. Okay? And by the way, if just to teach the buzzword, so I taught the buzzword of holographic entropy cone, which you've probably seen in titles of papers on the archive. And now I'm going to teach you this word contraction map, which often appears in abstracts of papers that have holographic entropy cone in the title. And a contraction map is just a cut-paste argument. Okay, so because of this, we can actually put the search for inequalities on a computer. And this is what we know so far. First of all, so I gave you inequalities for 2 and 3 parties. For 4, there's no new ones. For up to 4, there's no new ones besides the ones that I wrote. For 5 parties, there's 5 additional inequalities. Of course, you can do, when I say additional inequalities, you can do things like adding these to each other or taking permutations of the parties and so on. But this is sort of a basis of inequalities. And that's all. So there's no more than these 5. For 6 parties, so far there's about 1,800 known additional inequalities, but all indications are that there are many, many more actually. Just people got tired of running their computer programs to look for more. No one really knows how many more there are. But then if you're very clever, you can construct actually infinite families. So there are 2 known infinite families for arbitrarily large n of these inequalities that are, and again, these are independent. So none of these are like some linear combination of the other ones or something like that. These are all independent inequalities. And let me just repeat this fact that the proofs of these inequalities, surprisingly to me, involve essentially no physics input. Okay, they're just sort of like very, very kinematical facts about the holographic map. So they are ways in which quantum information theory is built into holography, but somehow, again, in this very kinematic way. Now, you might add, so for the first three inequalities, subadditivity, strong subadditivity, and MMI, I wrote them in terms of the mutual information, which hopefully made their meaning a little bit clearer. And you might ask me to do the same thing for these. Unfortunately, it's not known, it doesn't really clear them up very much just to write them in terms of the mutual information, and it's not known how to write them in some like very clean way that would illuminate their quantum information meaning. So the quantum information meaning of these inequalities is still somewhat mysterious, although people have made various conjectures. Okay, this leads to the following point. So 250 years and 2 days ago, Thomas Jefferson and his collaborators posted a paper on the archive with the claim that all men are created equal. And so the point, he did not say in that document, all RT inequalities are created equal. Okay, so he knew what he was talking about because all RT inequalities are not created equal. There's two very different classes of them. And the first class are the first two I gave you. And those are subadditivity and strong subadditivity. What makes them different from the others is that they are true for general quantum states. Okay? And that makes them checks on the RT formula. All of the rest are not true for general quantum states. It's very, very easy to find counterexamples. And here's some counterexamples. So every single one of those other inequalities is violated by every single state on this list. The simplest is just a GHZ state. As an example, MMI, superadditivity of mutual information. In a GHZ state, the mutual information between any party and any other party, or any subset and any other subset, is log 2. And that is not log 2 is not a superadditive function because log 2 is not greater than or equal to 2 log 2. Okay? And if you ask me, I often get this question, well, what about quantum field theories? No, sorry, quantum field theories do not obey these inequalities either. Just free scalar fields violate them. Basically, every free scalar field violates them. And the reason is that the zero mode or the long wavelength mode kind of makes the state into a GHZ-like state. It's a common it's a common mode that's shared by all of the different spatial regions, and that makes the entanglement GHZ-like. And for similar reasons, ground states with topological order, like the ground state of the toric code and so on, for essentially the same reason, violates every single one of these inequalities. And now we're getting, if you remember from the first slide of the talk, we had those three restrictions on the validity of the RT formula. The first one was large n. So what happens if you relax large n and you include the 1/n corrections, which are bulk corrections which are quantum corrections from the bulk viewpoint? In the bulk, you have various fields, including scalar fields and other fields, and those fields will generically violate these inequalities, which means that if you saturate the inequality at leading order, you typically will violate it, or you can violate it, depending on what particular state you have and what fields you have, when you add those 1/n corrections, and that fuzzes out the entropy cone. So the boundaries of the entropy cone become a little bit fuzzy once you add the 1/n corrections, assuming that we're talking about a regime where the 1/n corrections are small. Okay. So this is very, very important to know when you're thinking about the meaning of these. It's not that as holographers we discovered a whole bunch of new facts about entanglement entropies that are true universally. They're not true universally, but on the other hand, they are true for some much larger class of states than just holographic static states, classical static states. And I think it's very interesting to look at the class of states that obey these inequalities, which is larger than you might expect. Well, first off, are the states that obey it because they essentially obey some version of the RT formula. Okay, so an example is, so first of all, in a recent paper, we made a conjecture that asymptotically flat spacetimes connected by wormholes obey, in the static case, obey a version of the RT formula. And if that conjecture is true, then they necessarily obey all of these inequalities. Okay, where now the entropies are the entropies of the asymptotically flat regions. Those are the parties in the multi-party entanglement. Perfect tensor states is a certain class of states that's designed for quantum information purposes and whose entropies can be computed as min cuts on a very simple graph, star graph. Slightly more complicated, but in the same vein, the page curve, which tells you the entropy of any subsystem of a large quantum system in a random state, in a Haar random state. The page curve just goes up until you have a fraction half of your system and of your full system and then down again. If you use the page curve to compute your entropies, it will obey all of these RT inequalities. And the reason is that, again, there's a star graph that computes the page curve basically for you. Again, slightly more complicated are random tensor networks, which are designed to obey the RT formula, again, by min cuts on a graph. And then a more recent example from my colleague Brian Swingle at Brandeis, they designed a class of states which, again, are related to graphs. In this case, it's not a tensor network. The Hilbert spaces are on the vertices, not the edges of the graph. And what you do is you do a quench that puts the state of the vertices into basically a collective squeeze state, and then you do a projective measurement on all the internal vertices. And as a result, you get a state that exactly obeys the RT formula for all of the external vertices. So it's designed, again, to obey the RT formula, and therefore it obeys all of these inequalities. So that's fine. Of course, we know why all of these states obey these inequalities, at least on this superficial level. But what's interesting is that there are other examples that don't obviously obey the RT formula, yet seem to obey these inequalities. And that, to me, is more interesting. It's also true that the examples I'm going to give you are more speculative, and we know less about them. So first of all, what about that second restriction I made, that you have to be at strong coupling, in other words, be in Einstein gravity? If I relax that, then do I still obey these inequalities? And the answer is we don't know. We have a little bit of evidence from very simple examples. Again, to ask the question, since if you're talking about perturbative corrections, let's say alpha prime corrections or higher derivative corrections to the bulk action, then you would really be asking about a situation where without the corrections, you're saturating the inequality, and then you're asking about what direction the perturbation moves you in. And from what we can tell, the perturbation doesn't move you in a direction to violate the inequality, although it hasn't been studied systematically. You can be more bold and say, well, what if I just actually make alpha prime finite? In other words, I'm talking about some CFT, which is large C, but not, or large N, but not strong coupling. And there we have, of course, even less evidence, although thanks to work by Tom Hartman from a while ago, we actually do know how to calculate that in large CCFTs in 1+1 dimension that have vacuum block that obey a property called vacuum block dominance. And in that case, it does obey the inequalities, but for a bit of a simple reason. It obeys the inequalities because the entropies are equal to those you would have computed by RT, even though you shouldn't be applying RT because they're not at strong coupling. But here, I mean, an example of such things are symmetric product orbifolds at large N. And I want to highlight that example because it shows that this issue is not a integrable versus chaotic theory issue, because the symmetric product orbifolds are integrable, and yet they still seem to obey the inequalities. Maybe even more intriguing is SYK, where now we're talking about the entanglement entropies of groups of fermions. As far as I know, although SYK has a holographic dual in the form of JT gravity that can be used to compute entropies when you just have like a two-sided black hole, this is not that. Here we're talking about groups of fermions, and as far as I know, that is not computed by an RT formula. But as an empirical fact, at least to the extent that it's been investigated, it seems to obey the inequalities. The answer may be that it's that really there is some graph behind it. Okay. So this is the typical of the title, and the picture here is that when a random state is actually is an example of a holographic states. Those are subsets of large N states. When you just talk about general quantum mechanical states, the big yellow rectangle, there the inequalities are not true. With the smaller purple egg, they are, what's going on with large n? Is there some subset there that do obey the inequalities? Okay, so the big questions in this field, first of all, as a mathematical question, what's the general structure or pattern of these inequalities? Physics question, what are they telling us about semi-classical states in quantum gravity? A sharp question here is, are they valid beyond the Einstein gravity or strong coupling limit, or for some even larger class of large n states, as I alluded to? And finally, are they valid in non-static states? And the rest of the talk, I know I don't have much time left, I will briefly talk about what's known about that. But first I want to just give you guys a quote that I like, that you don't have to trust me that this is an interesting set of problems, because on my last grant application, which was partly about this subject, one of the referees came back with this little bit of poetry. This topic is admittedly a bit niche, but it has remained a stubbornly fruitful area of study. So I love that. So it's stubbornly fruitful. What could you ask for more? Okay, so if we talk about non-static states, then we have to upgrade to the HRT formula, where we restrict to extremal surfaces. These are codimension 2 extremal surfaces. And and you can ask, do the inequalities hold? Well, subadditivity, no problem, the same proof goes through. But with strong subadditivity, you stub your toe, because now these are codimension 2 surfaces. They don't generically intersect anymore. Even if they do intersect, these candidate surfaces you made, gamma tilde B and gamma tilde ABC, are not extremal anymore, so they're not in the set of things you're minimizing on. Nonetheless, people have succeeded in proving that the HRT formula does obey strong subadditivity, and that's all, some of it is quite old, some of it is more recent, so we now actually have 3 different proofs of that using different techniques. But the important thing I want to say here is that now we're in the world of physics, because these proofs these are GR theorems. They require standard GR assumptions of the same kind you use to prove the Penrose singularity theorem or Hawking area theorem, et cetera, this kind of GR theorem, okay? And so this shows that now the quantum information that's built into GR via holography actually knows something about the dynamics, knows something about the physics of the bulk. That, to me, makes it more interesting. And it makes it an even more interesting question whether the higher entropy inequalities are obeyed by the HRT formula. And here we don't know the answer to this question. I think it's a fascinating question, both from the point of view of understanding holography better, and from the point of view of just general relativity as a general relativity question. And let me just quickly go through the evidence that we have. So we know that MMI is true. So that's one of these higher inequalities. There's a certain regime where it reduces to an RT-like formula, where and therefore the inequalities hold. And then we've studied it extensively in 2+1 dimensions, looking for counterexamples and gotten partial proofs. And finally, most recently, we've proved that there's a large class of saturating configurations that cannot be violated in a very non-trivial way by deforming the configuration. So I don't have time to show you that, but basically you start with configurations that are all on a common light cone. That gives you something called a generalized Markov state, and then you attempt to deform the metric, and you're constrained by the physics. And the physics here is in the form of the Einstein equation, the null energy condition, which gives you focusing. And that tells you that the deformation of the area has to obey a certain concavity property. And the concavity property together with the combinatorial property of the inequality. So there's a conspiracy here between the physics and the inequality. So the physics provides the concavity, then the inequality provides a certain combinatorial property, and that saves the inequality. And so we prove that every higher inequality obeys this combinatorial property, and therefore you cannot violate an RT inequality by deforming one of these things. And this is a very large class of saturating configurations. Okay? Now, I just want to advertise that I think as open problems in GR go, I think this is a beautiful one. We've spent some time trying to prove it. I think one nice idea for trying to prove it, although we haven't been able to get it to work, so maybe it's not true, which would also be very interesting, is to produce a graph model. So if you remember, we got all those nice properties from reducing the RT formula to a graph model. Do we have a graph model for HRT? If we did, I think it would actually illuminate this long-standing problem of tensor networks for non-static states. But the bottom line is we seem to be missing some tools for proving GR theorems. And these are, again, the open problems in the field. Thank you so much.
We have some time for some questions.
Thanks for the presentation. I was wondering if you could elaborate a bit more on the saturated cases. What are these objects, and what would happen if you consider non-saturated objects, if that makes sense?
So you mean in the last part of the talk?
Yeah, but I think you talk about that also a bit in the middle, about saturated objects.
Yeah, so I mean, okay, so we have this cone, the entropy cone, which is delineated by these inequalities. And anytime you have an inequality, you should ask yourself under what conditions it's saturated. So those are very interesting configurations, particularly if you're interested in attempting to violate the inequality. So when you're sitting on that face of the cone, meaning you've saturated at least one inequality, then you can ask, well, now if I add 1/c corrections or alpha prime corrections, which direction does it push me? Or if I add time dependence, which direction does it push me? So that's where we often, when we're studying these things, that's where we often live. But I'm not sure if I answered your question.
So saturation is that something is concentrated on the edge of the cone.
It means that at least one of these inequalities is saturated, means the two sides are equal instead of one being greater than the other.
Okay.
Yeah.
And then the cases of non-saturated, can you study those?
Well, there you're in the middle. So if you're not saturating any of the inequalities, then you're sitting in the middle of the cone. And that's fine, nothing wrong with that. But it's not interesting from the point of view of testing whether some effect moves you outside the cone.
Okay.
Yeah. Hi. Thanks very much for your talk here. So you find on the computer you have this very large number of inequalities and so on, and you told them that they were not obvious sums or whatever differences. But is it obvious that they're independent, completely independent from one another, or would it be possible to construct them by looking at the subset of the ones at the lower level, so to speak?
Yeah, so all of the ones I showed you have been proven to be independent. So every single inequality I showed you or talked about has been proven to be independent. So these are what are called primitive inequalities, so they cannot be written as sums of any other inequalities.
So when you find an infinite number of them, you have proof that you told them in some cases that there's an infinite number of them for sufficiently large n.
Yeah.
They've proven to be independent from one another.
That's correct. And independent from any other inequality, including ones that have not been discovered yet. So it's actually very hard. That's actually much harder than discovering a new inequality. It's proving that it's independent of other inequalities.
I would expect
yeah, those are actually quite hard.
Thank you very much.
I was wondering whether you can interpret your higher inequalities in terms of some positivity or multipartite entanglement.
Yeah, so there's a very interesting, okay, so these are statements about multipartite entanglement. These are quantitative statements that constrain the multipartite entanglement. For example, MMI shows you that this quantity called the tripartite information is non-positive, and that is a measure of multipartite entanglement, or yeah, it can be combined with other things to get a measure of multipartite entanglement. Now, the problem is that there are many, many different measures of multipartite entanglement, and it's not and most of them we can't calculate in holography. So, these things are telling us something about the nature of multipartite entanglement, but nobody has quite distilled. So I think what would be nice would be something like an ansatz for the state that automatically implies all of the inequalities and that would hold for holographic states. So an ansatz saying you're going to have this many, GHZs or this many perfect tensors or this many some other more complicated thing, and that when you feed that ansatz into the inequalities, they're automatically, that would explain them, right? And that would also say all holographic states are of this form. We've conjectured such a thing for the tripartite and four-party case. It's not clear whether it's true or not, but anyway, that's what we would like.
Last question, Daniel.
Hi. Yeah, so I was just wanting to understand a little bit better what you mean by semi-classical states. So for example, in any situation where one of these inequalities is saturated, I can just add some matter to the bulk in a W state or something, and that'll violate the inequality. And I can even make it large by having a lot of matter or a black hole or something. And so, so I always thought that these inequalities are a bit suspicious for this reason.
Yeah, so we're in, so by semi-classical, I mean basically that the 1/n expansion is under control, that the corrections are smaller than the leading term. Now, you could quibble with that. Maybe I should invent a new word, or there's another word. So if you have a situation like, a black hole that's past its page time and, the universe is filled with radiation, and you look at the whole universe, it's true that then, these inequalities could be violated. And you could say, well, that's semi-classical. So by semi-classical, what I meant is just that the corrections are smaller than the leading term. And I think that is an interesting class of states. It doesn't include certain things like very old black holes, but includes like most things. Yeah, for the same reason that classical mechanics is useful. Yeah, I think that it's a useful and interesting set of states.
Okay. In the interest of time, I don't think I can take any other question. So let's thank Matt again.
Thank you.
So our next speaker is Dr. I checked with him whether he's a professor or a doctor. Dr. Elliot Yesto from MIT Harvard, and we'll talk about obstructions to space-time emergence.
All right. Thank you very much to the organizers for inviting me here. It's really an honor to be here. So today I will be talking about obstructions to space-time emergence. And this is based on various recent works, especially this recent paper with Netta Engelhardt that sort of unifies this previous work together. In holography, space-time is not a fundamental concept. Rather, we know that it's emergent from the fundamental Hilbert space of the theory, at least in our up to modern days understanding. And more precisely, it is EFT on a space-time background that is emergent. Then a natural question to ask is which semi-classical space-time geometries can emerge holographically? And the easiest answer to this, the thing that we understood since the early days of ADS-CFT, is spacetimes like this that can just be recovered by using the HKLL map followed by the extrapolate dictionary. So for example, if I take this double-sided ADS-Schwarzschild, I can just do HKLL on the two exteriors and then evolve everything with the equations of motion. But then we know that there's many more spacetimes that have asymptotically ADS boundary conditions. For example, there's this long wormhole spacetime here, and I can do HKLL on the exterior, but for the interior region, it's more complicated. We can't just use HKLL. But by now, we know that actually spacetimes like this are fine. A lot more spacetimes can emerge holographically, and this is basically the statement that the entanglement wedge can be a lot larger than the causal wedge in holography. So knowing this, we could get hopeful, and we could ask, does this fact lift all restrictions on spacetime emergence from holography using the paradigm that we currently have? Well, in order to answer this question, it's useful to ask, when do we know there's a problem with spacetime emergence? And until recently, the cases we knew were failures of emergence when there was a pathology within the bulk EFT itself. So for example, we don't expect spacetime to emerge near a singularity when there's large curvature effects. And more recently, there have also been cases where spacetime is non-emergent after performing an exponentially complex operation on the EFT. Here, the proposal being that exponential complexity makes also the EFT leaves its regime of validity. But those two things are sort of breakdown of EFT type of things. So the question that I will ask today is more refined. It is, can a spacetime always emerge from the usual rules of holography when there's no such problem with effective field theory itself, at least when we have an asymptotic boundary around? It turns out that in the recent years, there's at least been two examples of spacetimes that have been puzzling from this point of view. We found failures of the usual rules of emergence with these two examples. The first example is a closed universe entangled with ADS at order 1. So you can see this as a general setup, but something very close to this was constructed through the gravitational path integral in this paper. The second example is the fully evaporated black hole. So let's try to think about these two examples. In this closed universe entangled with ADS at order 1, if we look at the time reflection symmetric slice, it doesn't really look like there's any large curvatures going on or anything like that, and there's also like no real complexity. So for example, here, you know, everything's low curvature, the ADS low curvature, so there's no obvious problem with effective field theory on this spacetime. Similarly, for the fully evaporated black hole, so here we're looking at a slice at full evaporation, so it's the union of this purple slice here and this green slice here. And this purple slice is completely semi-classical. The green slice is almost everywhere semi-classical, except for this one little point here where it meets the singularity. But that's just a small portion of the slice. Most of the slice is actually semi-classical. So in those two examples, it looks like semi-classics are mostly fine, and yet we found problems. So today what I will ask is, what are these problems, and what is the general reason behind them? So of course, since I've been telling you about spacetime emergence since the beginning of the talk, I need to really tell you what I mean by spacetime emergence. And I will do this by studying these examples through different languages that have been useful to think about the emergence of spacetime in holography. The first language is the language of the large N limit of ADS-CFT, and the second language is the language of holographic maps. And then once we've described these examples through these two languages and seen how we can find issues, I will comment on the role of the area term in spacetime emergence. So first, let's try to think about how one describes spacetime emergence in the context of the large N limit of ADS-CFT. Well, the usual game when you want to talk about the emergence of spacetime is that you want to compare two descriptions of physics. The first description is what I will refer to as the effective description, and it is an EFT on some bulk spacetime. So that's the thing that you would like to emerge. And the second description is the fundamental description of the physics. So that's the exact UV-complete description of the system. And then usually what we say is that the effective description emerges from the fundamental description if the two become close in the semi-classical limit of the fundamental description. So for example, in the case of the large N limit of ADS-CFT, what I mean here is that the effective description is the large N bulk EFT, and the fundamental description is the finite N boundary CFT. And the statement that the bulk EFT emerges from the finite N boundary CFT is just that under the holographic dictionary, they become close as N goes to infinity. Now, one thing that I want to stress here and that I'll come back to at the end of the talk is that this is an objective notion. What you do here is that you fix once and for all the boundary CFT, for example, in ADS-CFT, and then you say, well, can I recover the physics in the bulk EFT from the large N limit of that theory? But it's fixed once and for all. Okay, so let's try to make this a bit more precise. What is the effective description in the case of ADS-CFT? Well, we want it to be, we want it to be the, we want it to be an effective description on a given background put in some pure state that I'm going to call psi. And I want to ask whether this emerges holographically. So now the fundamental description is really a sequence of fundamental descriptions. It's a sequence of boundary pure states, psi n, that I take at finite values of n. And then what I say is, is that psi is emergent. Sorry for the slides, I don't know what's going on. I say that psi is emergent from the sequence of these finite n states psi n, if for any operator O of the bulk effective field theory, its sequence of finite n reconstructions satisfies this identity. So this, so this identity here means that as I take the large N limit, I take a bulk operator O here, and I map it to the to its finite n reconstruction, this operator On, and then I ask that the large n limit of the correlation functions of On in the state psi n converge towards the expectation value of O in the bulk. So you should see this as a condition that the correlation functions of bulk fields can be recovered from the boundary in the large n limit. So of course, since I want to probe this emergence condition, I need to tell you, given a bulk operator O, how I reconstruct it at finite n on the boundary with an operator On. So what are these boundary reconstructions, On? Well, they're complicated in general, but there's one case where they're easy, which is the case where O is in the causal wedge of the geometry. Because in that case, I can just reconstruct the bulk operator by using HKLL reconstruction and the extrapolate dictionary, as I said before. So, for example, in the case of this long wormhole spacetime here that we looked at in the beginning, if my bulk operator O happens to be in one of these blue regions, I can just reconstruct it on the boundary by using the extrapolate dictionary of ADS-CFT. So if I can use the extrapolate dictionary of ADS-CFT, then the boundary reconstruct of the bulk operator O must be an n-independent function of single trace operators normalized by its one-point function. Okay. So now we can look at the case of a closed universe entangled with ADS, which was our case of interest in the beginning of the talk. So in that case, the causal wedge of this geometry is just the ADS region. And the large n state of the ADS fields, if it exists, is determined by large n limits of correlators of single trace operators. So if I take the large n limit of correlators of single trace operators, I'm supposed to recover what's going on in this ADS region. Now, if the geometry is emergent at large n, I apologize for the slides, I think there's a technical problem here. Then the algebra of large n single trace operators is in an overall mixed state. Sorry, this word is supposed to say mixed. And that means that they are entangled to the closed universe at large n. On the other hand, the other important statement is that the boundary dual of this state has order n to the 0 energy and entropy. So that's an observation that was made in this paper. You can show this in some general gravitational path integral setups, but there's also other arguments how you can show it. So now here is the catch. I was able to show the following theorem, which says the following. Suppose that the correlators of single trace operators of a sequence of pure CFT states of order n to the 0 energy have a large n limit, then the limit correlators of these operators are those of a pure state on ADS. So for a sequence of pure states of order n to the 0 energy, this means that either the large n state of single trace operators is pure or it does not exist. And what we said before is that in the case of this closed universe entangled with ADS, we want the large n state of the single trace operators to really be in an overall mixed state, okay? And what this theorem tells you is that in the large n limit, for states that could potentially prepare this closed universe, either they are in a pure state or the limit does not exist. So in any way, this rules out the emergence of a closed universe entangled with the ADS in the sense of the strict large n limit. And then the subsequent papers actually provided evidence for the lack of existence of a large n limit in the case of some explicit path integral preparations. Okay, so this is how, by this no-go theorem that tells you that a mixed state cannot emerge in the ADS region, you can basically show that you cannot have the emergence of such a geometry in the strict large n limit. Now I want to move on to a second case, which is the case of holographic maps. So first I described the emergence of spacetime through the language of the large n limit, but it turns out that we had this second example, which was the example of the fully evaporated black hole. And for this example, it's a bit more complicated to think about it in terms of the large n limit, so I'm going to explain another framework in which we can think about spacetime emergence, which is the framework of holographic maps. And more precisely, I'll explain how this framework allows to tackle both cases and once again find problems with the emergence of spacetime. So in quantum information models, to define spacetime emergence, we use a so-called bulk to boundary map. This is a map that maps two Hilbert spaces, a Hilbert space H code and a Hilbert space H physical. So recall that we said in the beginning that the game in spacetime emergence is to compare two descriptions of physics. One is the effective description and the other one is the fundamental description. And that's exactly what this map is meant to do. So for example, let's say that I look at a semi-classical geometry that is a bulk of is a slice of space, and I regulate it with some blue qubits here. So this Hilbert space H code is the Hilbert space of the effective description. And what it does is that it denotes the degrees of freedom of the regulated bulk EFT with a UV cutoff taken well above the Planck scale on a bulk slice. So that's the Hilbert space that's supposed to describe our effective description. And then we have another Hilbert space, which is the range of this map, which is H physical, and that's supposed to be the fundamental description. So that's the UV complete Hilbert space, and in ADS CFT, it's the finite N CFT Hilbert space. And this map maps the effective description to the fundamental description, and now the game is to ask, what properties of this map guarantees that we can say that the effective description emerges from the fundamental description. So in order to ask this question, I need to tell you a little bit more about the form of this holographic map in general, and there's a proposal for it, which is the Python's lunch proposal. So the idea of the Python's lunch proposal is that this holographic map is a succession of isometries and non-isometries. The idea is really simple, is that for a general spatial slice, it's going to grow and then go down again and then grow and then go down again. And basically every time the slice grows, the map is isometric, and every time the slice goes down, the map is non-isometric. And the key for today is that outside of the outermost quantum extremal surface, so in this exterior region here, the holographic map is always an isometry. In particular, this implies that the holographic map is always an isometry on the causal wedge, which is the region which you can show is always contained outside the outermost quantum extremal surface. Okay, so now that I've explained to you the form of this holographic map, I can define what I mean by emergence under a holographic map. Given a holographic map V, we say that this code subspace H code is emergent from the physical Hilbert space if for all pure states in the code subspace, their inner products are approximately well preserved by the holographic map. This is basically the analog of preserving correlation functions in the large N framework. In the large N framework, we said that emergence meant that when we took the large N limits, we preserved correlation functions. Well, here it's the same thing. It's that inner products are approximately well preserved by this holographic map. Now, this is good for a lot of intents and purposes, but actually sometimes it's useful to refine this criterion to a more detailed one, because the recent progress on the information paradox inspired us to slightly modify this criterion. So the idea is that inner product preservation under this holographic map should only really hold with high probability for EFT states that have sub-exponential complexity in 1/G. Okay, it should not hold for all of the EFT states. And the interpretation, as I was saying in the beginning, is that effective field theory could break down at high complexity, and therefore we should not ask for the emergence of high complexity operations. So just as a summary, we have two frameworks. We have this large N framework, which says that EFT bulk operators map to finite N boundary operators. And in the holographic map framework, the statement is just that we have this code subspace, which describes the regulated EFT, and that maps to the physical Hilbert space. The emergence condition in the large N framework is that the correlators of finite N representatives of bulk operators asymptote to those of the bulk operators in the EFT. And in the holographic map framework is just approximate preservation of inner products for low complexity states. And finally, the fact that sometimes reconstruction is really easy when you have the HKLL map at hand becomes the fact that the holographic map is an isometry outside of the outermost quantum extremal surface. Okay, so now let's try to apply this framework of holographic maps to ask what goes wrong in this case of the closed universe entangled with ADS that we found a problem with the emergence of in the context of the large N limit. So what is the form of the holographic map for this geometry? Well, we can just apply the Python's lunch proposal. So first, we have a code subspace, which describes the ADS region and the closed universe. That's our effective description. So it's a tensor product of the two. And then we have the finite N CFT Hilbert space, which is the fundamental description. And so the map should map one to the other. Now, because of the Python's lunch, we've just said that for the causal wedge, the holographic map is an isometry. So that means that here, this map V, HKLL, which acts on these red qubits that live in the ADS region, is an isometry. On the other hand, beyond this causal wedge, we have a Python's lunch. So here it's actually as non-isometric as it can get, because the whole slice shrinks to get completely disconnected from the ADS region. So in terms of Python's lunch proposal, this is translated into the fact that the closed universe gets projected onto one state after applying a random orthogonal matrix. And of course, this fact that you project onto one state is very related to the statement that we heard earlier about today, that the Hilbert space of a closed universe is one-dimensional. And then the question is, how does the form of this map tell us about a failure of emergence? Well, we said that if we want emergence, we need to preserve approximately inner products of all of the low complexity states in this geometry. So let's try to find one where we can't preserve the inner products. What you can do for this is to do a so-called swap test. So what the swap test does is the following. The trick is to double the system. So now you consider 2 copies of this closed universe entangled with ADS. And what you do is that in the effective description, you swap the ADS regions. So you only swap these red qubits here. You don't swap the closed universe. That's done at the level of the effective description. So you just swap these regions. Now the key point is that in the semi-classical description, so in this effective description, we like to use the swap test because it computes an entropy. It computes e to the minus the second Renyi entropy of this state that is supposed to be entangled between the closed universe and the ADS region. But then what you can show, essentially due to this complete projection onto one state, is that after applying the holographic map, the inner product between a state and its swap is not close to this value at all. In fact, it's close to 1 with an order 1 fluctuation. So if you recall that our condition for emergence under a holographic map was that inner products were approximately well preserved by the holographic map up to exponentially small errors, well, that means that here we found the failure of this condition. So since the swap operator is not a complex operator, we can once again conclude that there is a failure of the standard paradigm of emergence for this geometry. The nice thing about this holographic map way of thinking about things is that there's actually an exactly similar way to think about the second example that I was telling you about in the beginning, which is the example of the fully evaporated black hole. Indeed, there's a close analogy between the 2 geometry because in both cases, you have 2 things that are disconnected. So the analog of the ADS region in the case of the fully evaporated black hole is the radiation. So that's this purple slice here, the outside. And then the analog of the closed universe is the interior, which is this green portion here. So really, the statement is very close. We have 2 disconnected things that are entangled. The only difference is that the entanglement between the interior and the exterior in Hawking's picture of black hole evaporation is parametrically large in 1/g at full evaporation. And that's because you have parametrically many qubits of radiation escaping the black hole. But basically, that doesn't affect this swap argument too much. And in fact, we can generalize this to the fully evaporated black hole. So the idea is that the tensor network model that you write following the Python's launch proposal for the fully evaporated black hole works exactly the same way as it did in the case before. So you just apply an isometry to the radiation. In fact, in that case, it's just an identity map. And you project all of the interior onto one state. And then, just like when we said that if we swapped all the ADS all of the qubits in the ADS regions together, once we applied the holographic map, we found a big discrepancy of inner products. Here we actually find the same thing. There's a big difference in inner products between the effective and fundamental descriptions due to this swap operator. There's a really simple way of thinking about it physically, which is that because by unitarity of evaporation, the purity of the radiation is 1 at full evaporation, whereas in Hawking picture, it should really be exponentially small, there's a big discrepancy between these 2 numbers. Now, as I said, there's this one difference that there's a parametrically large amount of entanglement between the interior and the exterior. But basically, what this means is that now the swap operator will not be an operator of order 1 complexity because it swaps a parametrically large number of qubits. But nonetheless, it's still an operator of polynomial complexity. It's not an exponentially complex operator. So under the paradigm that we should allow in effective field theory all sub-exponentially complex operations, this swap counts. And we've still diagnosed the failure of emergence there. Okay, so at this stage, what we found is that for both this closed universe entangled with ADS and for the fully evaporated black hole, there are failures of the usual conditions that we require for space-time emergence in holography. So now I want to ask, what is the general reason behind this? So what is the common issue between these 2 cases? Well, in order to see what was the common issue between these 2 situations, it is useful to look at the space-time geometry. And really, there's something that I've hinted at several times, which is not that hard to see, which is that there's a common point between both cases, which is that there is a non-trivial surface that is homologous to the boundary and that has 0 area. So here, it is just the empty set that disconnects this closed universe from the ADS region. And here, it is the empty set that disconnects the interior from the exterior and the radiation. So, it seems natural to say that, okay, maybe having such surfaces that have zero or small area could be the diagnostic of these new failures of emergence at polynomial complexity that we found today. Well, at this stage, you could get a bit nervous because notoriously, the area term in holography is not usually to be well defined on its own. Rather, it depends on a choice of cutoff. And rather, it is really the sum of the area term and the bulk entanglement term, so the generalized entropy, that is believed to be UV finite. So we could say that maybe, a good diagnostic would be that there's these types of failures that happen whenever you have a surface that is homologous to the full fundamental description and that has a very small generalized entropy. But the example of the fully evaporated black hole shows that this cannot quite work. And the reason why it cannot quite work is because at full evaporation, in Hawking's picture, there's a parametrically large amount of bulk entanglement between the interior and the exterior, so the generalized entropy is actually large. And nonetheless, we still found a problem with this swap test. So here, what we learned from this example is that problems can still arise when the generalized entropy is large if the area is small. So how can the area term, which is known to be cutoff dependent, decide whether emergence works? Well, you have to remember that in the holographic map paradigm, we have a map that goes from a code subspace to a physical Hilbert space, and the code subspace is supposed to model an effective description of the physics that we are trying to make emerge. And the key point is that this code subspace, which is really what we are probing the emergence of, is also itself dependent on the choice of cutoff. It turns out that actually once we prescribe the code subspace, we can define an area term for a surface X as the generalized entropy of the least entangled code subspace state through X. So once you get to choose a code subspace, then you can define an area term that is associated to the geometry by essentially doing what you guess. So this is the simplest things. There's these papers that have much smarter ways of defining the area term, but this will be enough for me today. So imagine you have this bag of gold type spacetime and you want to define an area term associated to the surface X. Well, what you can do is first prescribe a cutoff. So you choose a code subspace which determines which qubits you put in your effective field theory, and then you disentangle all of them through X. And the remaining generalized entropy is the area term. So what is the role of the area term in this swap test argument that I presented? Well, let's try to run a similar swap test example argument in this bag of gold geometry here. So we're going to consider an entangled bulk state through this red QES X. And we're going to ask when swapping the outer regions, so these regions here, would amount to a problem of emergence of the kind that I described today. Well, the key point here is that this swap is really an effective field theory operations. In effective field theory, we are allowed to swap these blue qubits, but we're not allowed to swap the areas. So what we learned from this swap argument, for example, in the fully evaporated black hole, is that if no generalized entropy is hidden away into the area term, it becomes sub-exponentially complex to detect failures of emergence, even if the EFT entropy is large, because then you can do this swap test, and when you map it to the fundamental description, it will return a value close to 1. But on the other hand, you can't swap these area degrees of freedom because they're not part of effective field theory. So these degrees of freedom cannot be swapped within effective field theory, and instead they are hidden into the background. And actually, you can show that if you hide enough of these degrees of freedom carrying the generalized entropy of the surface X into the area term, then the analogous swap test that you would do on the outside regions would only be able to return for you an exponentially small value. So basically what happens here is that whenever I'm not hiding enough degrees of freedom into the area term, I can falsify the preservation of inner products with this sub-exponentially complex operation swap. Actually, using this, we were able to show a general result, which says that assuming a Python's lunch form for the holographic map, this condition of emergence of approximate preservation of inner products is violated for sub-exponential states if and only if there is a surface that is homologous to the full fundamental description and that has area term that is very small. So order log 1 over g turns out to be the exact bound. And this basically comes from just a generalization of this swap argument to a general Python's lunch dense network. So this led us to the following proposal, which is that given a code subspace and a map that maps it to the fundamental description, we propose that the global space-time picture fails to emerge from a pure state if and only if there exists a non-minimal quantum extremal surface for some state in the code subspace that satisfies the following. First, it is homologous to the full fundamental description. So here, for example, in this bag of gold, this surface X is homologous to the full fundamental description. And second, its area term is too small. So we have this precise condition on the area term here. And then if those two things happen, you see the types of failures of emergence that we saw in the two examples today. So as a conclusion, we saw today that even in situations where there is no obvious problem with EFT, such as large curvatures or high complexities, there can be failures of emergence due to surfaces homologous to the full fundamental descriptions of small area term, at least if we use the usual rules that we've been using until now to describe space-time emergence. And the lesson is that enough generalized entropy needs to remain inaccessible within the effective description in order to not detect failures of emergence. So this makes precise the statement that closed universe components cannot emerge from the traditional rules of ADS-CFT, because we see that whenever the area term is too small, your bag of gold almost completely disconnects from your fundamental description, and then you get something that kind of looks like a closed universe, and you have a problem. Now, of course, this talk was about clarifying what the problems were with the usual paradigm that we've been using until now to describe the emergence of spacetime. So either these holographic maps and sub-exponential complexity, or the large N limit of ADS-CFT, rather than the possible solutions. But of course, in the end of the day, we are all interested in describing the emergence of semi-classical physics inside a closed universe. So what we learned from this is that some modification of the traditional rules is needed. We need to change some rules. And this is actually, related to a lot of the things that Zhenbin was saying this morning at the end of his review. And in particular, one possibility that Zhenbin pointed out is that the notion of emergence that we talked about today is really an objective notion. You fix your boundary Hilbert space once and for all, and then you ask whether the semi-classical physics can emerge from that boundary Hilbert space. But maybe the notion of emergence in quantum gravity, when there's closed universes around, should really be more subjective. And this is, of course, related to the various proposals that we've heard about this morning, in particular about introducing observers into the description of the emergence of spacetime in closed universes. And this is, of course, also related to these different coarse graining procedures that we've heard about this morning, averaging over sources, over n, and so on. And actually, we could show that our diagnostic for when these criteria fail can be extended to the presence of an observer using the observer rules that were proposed in these papers. And then the analogous conditions of emergence to those that we saw today, upon this observer rule modification, can sometimes be restored. So we can restore a notion of space-time emergence in closed universes using these new developments. But I think it's fair to say that at this stage, there's a lot of proposals. Mathematically, they all seem kind of related, but there's a lot of debates about what they should really mean physically. And so there's a lot of questions to explore about this, about the new things we should do when there's closed universes around. And I'm really looking forward to talking about it with many of you this week. Thank you.
Yes.
So about these closed universes, there are different situations. One is like when the entanglement with the radiation, for example, is large, and one is like almost no entanglement, or let's say order one entanglement. So let me just focus on the case, let's say when the entanglement is large, for example, completely evaporated black hole. And you talk about the failure of emergence of space-time. I just want to ask that in that context, this failure of emergence, other than this kind of swap test inequality, any physical consequence? Let's say assume that if someone outside do some complicated enough things, presumably that already changed the interior, and so who can see any bizarre consequence or anything? Yeah.
Yeah, great. Thanks for the question. I was hoping to get a question like this. So the point, indeed, is that that is the potential resolution, right, that I was talking about here. The talk today was about, if we follow the usual rules that have been working for us until now, what do we find? What do we find? Well, we find a problem. But indeed, this is the right point, that at full evaporation, if you do the swap on the radiation, you're outside the black hole. So it's not like you can jump in and realize that, there's no black hole interior or whatever. It's really an objective notion of emergence that fails. It's the notion of emergence to an observer that's outside the whole space-time. But now you're right that, this objective notion of emergence is what we've been using so far, but it's not clear that it means anything physically to someone that jumps into the black hole. But what this example shows us is that we really need to take this into account. Because if we forget about this objectivity versus subjectivity distinction, then indeed we would just say there's a problem. But we don't want to say that there's a problem. So this is actually related to a point that we made with Netta and Daniel in our paper on complementarity, which is that if you start using these observer rules and asking for emergence being subjective rather than objective, then there's no problem because you find that there is emergence of the black hole interior to someone that jumps in. But this objective notion of emergence that just requires knowing the boundary Hilbert space is the thing that fails here. And I agree that the point should be that maybe this is not the right physical thing to think about. But this is the example that sort of pushes you into a corner about this.
In the interest of time, unfortunately, we cannot take any further questions. I've been told to wrap up the session, so let's thank Betty again.
So the next is gong show from 4:30.
Hello, it's working right? Sure.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
《尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
《尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, hello everyone. So the last item for today's agenda will be gong show. It will be 12 5-minute speeches by excellent young researchers. So before we start, I ask all gong show participants for today, please come to this part of the room. We are still missing some of the presenters. Please be sure you come in time. Okay, so our first presenter will be Ahmed Barbar, and we will start, and 5 minutes into his talk, you will hear a gong sound, and after the gong sound, next presenter would go to a stage. So there is no questions. All questions, please ask after the gong show ends. Thank you. Let's start.
So
My name is Ahmed. I will talk about a toy model of 3D gravity. Oh, sorry. Based on, if you take a TQFT, compact, semi-simple, nice, and you try to sum it over topologies, then you try to find out what is the boundary ensemble of CFTs. And this idea has been studied in the literature in various ways. But the key points that I want to emphasize in this approach is that the left-hand side, we want to sum over all topologies, not just handle bodies, not just the set of points. And the ensemble of CFTs, we really should think of it as an ensemble of topological boundary conditions of the bulk TQFT. So think of the bulk TQFT as a sim TFT for all these CFTs. And now the questions that we want to answer is, how do you sum over all topologies? Is that even possible? How do you even define the sum? And if you manage to do that, what will be the boundary ensemble? What will be the weights and so on? So basically, what is the measure on both sides? And so how do you sum over topologies? You basically, every compact oriented three manifold admits what's called the Hegert splitting. So if you have a closed manifold, you can split it into two handled bodies glued together across the splitting surface by a mapping class group transformation. If you have a manifold with boundary, you can do the same, but use a compression body instead of a handle body. So what is a compression body? Think of the Euclidean wormhole, but you attach more handles to one side, but not the other. And the idea is that if you make the splitting surface a surface of a very large genus, you'll be able to split pretty much any manifold you want. And so all we need to do is to insert this projector in the gluing, which will sum over all the gluing maps, and this will guarantee that we get all manifolds in the sum. Maybe more than once, but that's okay. And this gives us a universal way of calculating any amplitude, any gravitational amplitude we want, with the same projector, just use, compression bodies or handle bodies and so on. So how do you actually compute the sum? It needs to be regulated and so on. But you actually don't have to do it explicitly. This is a projector, so you can just rewrite it in terms of an orthogonal basis of the projected subspace. And in this case, one can show that as in the infinite genus limit, the states prepared by topological boundary conditions, they become orthogonal. Okay, so that we can show explicitly. And if you assume that there are no fake modular invariants at large genus, then that's basically a complete basis. And you can rewrite the projector in such a way. Okay, and now with this presentation of the projector, we can just compute any amplitude we want. And each term here factorizes the splitting. So you get a sum of factorizable terms. That's your ensemble. And so you can think of these states, the topological boundary conditions at infinite genus, as alpha states or alpha sectors. Okay, so now we need to worry about what is this ensemble weight. It's something we calculate at infinite genus. What is this overlap? And this overlap, it's a SimTFT sandwich, but both sides are now topological boundaries. And it's a partition function of a very special 2D TQFT, which you can write in this way. And where these are the quantum dimensions of the symmetry lines that level the symmetry boundary. Okay, so these are, it has the same symmetry as the corresponding CFT. And in the infinite genus limit, the quantum dimensions are, they're smaller, greater than or equal 1. So in the infinite genus limit, this basically counts how many ones you have. So how many invertible defects you have. So it's the size of the automorphism group of the topological boundary, or the algebra object that is corresponding to the topological boundary. And if you're a CFT person, these are basically the group of symmetries that commute with the chiral algebra associated with the TQFT. Okay, so think of the invertible Verlindi lines if you have a diagonal CFT. Here's a cute example which I'll skip. And just to summarize, in this toy model, both sides of the holographic duality are very natural sums. If you're a mathematician, you weigh things by 1/0 if they are isomorphism classes. And you can ask me later about how to write the bulk sum as a 1/0 kind of sum. There is a Bibi universe interpretation where these alpha states, the topological boundary conditions are alpha states, and the Bibi universe Hilbert space is basically the Hilbert space at infinite genus, or the mapping class group invariant subspace. And finally, it would be interesting to apply this to Versor TQFT. It's not obvious how to do that. But if things work in the same way, the analogy would imply that we get an ensemble of all CFTs weighted by the full size of the symmetry group. And that would be nice because non-holographic theories with higher symmetries will be tuned out. So I'll stop here, but thank you for your attention.
hello everyone. Yes. Hello everyone. First of all, thank you to the organizers who made this all possible. My name is Jackie, and today I'd like to tell you about a paper that I put out in May with my collaborator, Aiden Herdersen. And it's about inner horizon saddles in the gravitational path integral and a proposed weakening of the KSW criterion. I'm supposed to go up. Okay. So to begin, I'd like to state a key lesson that I think we've learned about quantum gravity in the past several years, which is that while it's easy to mistakenly overcount states in quantum gravity, for example, to think that the amount of information contained in a black hole is bigger than it actually is, we often get lucky. We often get lucky because corrections to this overcounting are often computed by saddles of the gravitational path integral rather than details of the UV completion. So of course, the most famous example of this is the black hole information paradox, where the naive number of states contained inside of the black hole is corrected by wormhole contributions, replica wormholes, or inner product wormholes. And another nice example of this appears in the computation of supersymmetric indices and holographic theories. And here the bulk corrections to the overcounting, the naive overcounting at large n, come from unstable giant graviton saddles, can come from unstable giant graviton saddles with a minus sign showing up. Okay, so with all these nice ideas in mind, I'd like to discuss a simpler setting, which is the context of just pure JT gravity. I hope that many people in this audience are familiar with this famous formula for the density of states at energy E in JT gravity, which is just given by this sinh. So of course we can take this sinh and split it out into two exponentials divided by a minus sign, separated by a minus sign. And we see that this formula actually has the schematic form that we were discussing on the previous slide. So this density of states, this number of states, is given by some first term, which provides a naive overcounting of the number of states. And then there's a correction term, which gives you the correct answer. And now you can ask, inspired by the previous slide, whether these two terms are associated with saddles of the gravitational path integral. And of course, the answer for the first term is yes. So if you just take the disk, the hyperbolic disk, in JT gravity and evaluate its on-shell action, you get this quantity here. But now you can ask whether, like in the previous examples I mentioned, this correction term is also computed by some gravitational saddle. And so in 2024, Kruthoff and Levine proposed that the answer is yes, and that there's some new gravitational saddle associated with this term. So basically, in my paper with Aiden, we study this saddle to death. And today, I would just like to give you 3 reasons why, in increasing order of importance, of why I think this saddle is interesting. So the first reason is that it's a really simple example of a saddle which contributes with a minus sign. And so we analyze how this minus sign appears just by studying the negative modes that arise in perturbation theory around this saddle. Okay, and again, going in increasing order of importance, another reason why I think this saddle is interesting is because it knows a bit about inner horizon physics of charged black holes. So in fact, we call this the inner horizon saddle. So let me explain why this knows about inner horizons. So this comes from, so the connection with inner horizons comes from viewing JT gravity as not as a theory of 2D gravity in its own right, but instead a theory which comes from dimensionally reducing Einstein gravity in the context of near-extremal black holes, and dimensionally reducing on the sphere to study an effective theory of near-extremal black holes. So in this context, the formula that we've been discussing just looks like the statement that the density of states of a near-extremal black hole is, at leading order, the Bekenstein-Hawking contribution given by the outer horizon area over 4G, but then it's corrected by a quantity which has to do with the inner horizon area. So that's the sense in which this saddle has to do with inner horizons. So here's a picture here. There's like the naive Bekenstein-Hawking answer, which plateaus in the near-extremal regime, but of course, famously, at extremality, the black hole density of states should drop to 0. And in this picture, it comes about because of the inner horizon approaching the outer horizon at extremality. Sorry, I'm almost done. Okay, so the third thing that I think is really interesting about this saddle is the fact that it's complex and it violates the KSW criterion. So we argue in our paper that it really has to contribute to the GPI, even though it violates the KSW criterion, and this motivates us to propose a weakening of the KSW criterion. So these are sort of a summary of the 3 things I talked about, and please talk to me if you're interested in any of those things. And I'm so sorry if I went over time.
thanks a lot to the organizers for giving me this opportunity to present a work. Today I'll talk about finite and BMN index across all vacuum sector. This is the work I've done with my supervisor, Professor Chiming Chang, and PhD student Kang Ning Liu from YMSC. Tsinghua University. So the key takeaway is that when we compute the finite and protected BMN index sector by sector, the entropically dominant sectors are suggested due to dressed black hole interpretations. So let me first recall the setting. The BMN matrix quantum mechanics is a mass deformation of the BFSS describing a DLC group M theory on the maximally supersymmetric plane wave background, and this deformation leads to flat reactions, giving a discrete spectrum and a family of fuzzy sphere supersymmetric vacua, and it also admits brain interpretations like multiplicities held fixed and the sizes of the irreducible blocks taken large, and the fuzzy sphere gives the spherical M2 brains, and in the complementary large multiplicity scaling, it describes the Lin-Maldacena geometric description and transverse M5 brains. And at strong coupling, it also has a confined phase connected to the Lin-Maldacena geometry and deconfined phase connected to the black hole geometry. So our main technical goal is to make the finite and BMN index computationally tractable across all vacuum sectors, and it's also a prerequisite for isolating genuinely finite in states of the fortuitous type. So the vacua in BMN matrix quantum mechanics are just the fuzzy spheres, and xi's are proportional to gi's, and xm equals to 0, and gi is an n-dimensional matrix representations of SU2, and we can decompose gi's into SU2 irreducible blocks with multiplicities, and this gives a partitions of the integer n. And now each partition defines a distinct vacuum sector, and the specific superselection sector index is the matrix integral, and this matrix integral projects onto the gauge invariant states under the k-node gauge group, and the total BMN index is the sum of contributions from all superselection sector index, and we have three complementary methods to compute the finite index, and we have symmetric group character expansion. This reduces this problem to a finite combinatorial sums, and the second is the residue expansion, where the contributing poles are organized by rooted trees for single node or single partition sector, and with a colored rooted tree generalizations for the multi-partition sector. The third is this relative fugacity projections or the constant term extractions from the integrand. So now we compute the BMN index, and we expand this index with equal fugacities, and we track the coefficient at charges near j equals to n square, and we see that for n equals to 2, 3, 4, we compute the entropy in the microcanonical ensemble, and we see that the sector summed entropy is dominated by single partition family. For n equals to 5 to 9, it's dominated by double partitions, and it also happens for largest individual contributions also. So here the main interesting point is this dominant switching, and the BMN index starts preferring sectors with non-trivial fuzzy sphere structures. Like for n equals to 5 to 9, the double partitions family is dominant, and this indicates that there is a non-trivial fuzzy sphere structure. Sometimes BMN index starts preferring. So now to interpret our results holographically, let's translate two BMN scaling variables. We have dimension full BMN T-hook coupling lambda and dimensionless BMN ratio lambda by mu cube. Here mu is the BMN mass parameter. So the D0 radial coordinate U has dimensions of energy, and the standard D0 scaling relations follows from the IMSY analysis, and we are in the control type 2 D0 supergravity region, where Q is between 1 and n to the power 10�7. And we can identify the boundary quantum mechanical energy scale as the BMN mass parameter, and the IMSY D0 scaling relation gives UH equals to mu Q to the power 1/5. Now for a dominant BMN vacuum sector, the largest fuzzy sphere component has this radial scale, which is UD2 equals to mu n max, and we can compare it with the D0 horizon scale, and it gives us this dimensionless comparison parameter, which is n max Q to the power -1/5. Now the D0 lies outside the horizon when this chi max is parametrically larger than 1, and Q should be less than n max to the power 5. So this relation is kind of a window between the bulk in picture and some finite and BMN index data. So the relevant parametric domain is now the intersection of this condition and the type 2 D0 supergravity condition, and we get n max to be larger than 1. So when the dominant BMN index sector satisfies this condition, then the bulk description should not be a pure D0 black hole alone, and we have the protected state should also retain macroscopic type 2 D2 brain degrees of freedom outside the horizon, giving a D2 dressed black hole picture. But there is a caveat here. So the evidence is that finite and the radial scale UH is inferred from strong coupling BMN scaling rather than from an explicit BPS solutions. So now we can compute the type 2 horizon entropy, and we see that it carries parametrically less entropy than the observed n square index entropy. So the remaining protected entropy should be tied to the macroscopic D2 brain degrees of freedom. So here we computed the entropy, and it lies between the n to the power 87 and n square. So the upper end n square lies near the boundary q equals to order 1. It's between the region perturbative SQM and type 2A D0 supergravity, and here type 2A description failed because curvature becomes string scale. And this makes the D2 Dress black hole picture may explain why no pure BPS black object asymptotic. Okay. Okay.
So hello everyone, I'm Kosei Fujiki from YITP. So first I would like to thank the organizers for giving me such a wonderful opportunity. So my talk title is Mulch Entropy after Local Quench in CFT and Holography. This talk is based on our recent work with Kenya Tasuki. So first, let me start with a brief review of a local quench and its holographic dual. So we consider the two-dimensional conformal field theory and insert the heavy local operator. And then we can calculate the real-time evolution of the entanglement entropy. And its holographic dual is described by a massive falling particle in the Poincare coordinates. And by calculating the back-reacted metric, we can obtain the real-time dependence of the geodesic length. And next, I would like to introduce mulch entropy, which is one of the strong candidates for a mulch-partite entanglement measure. And its definition comes from a natural generalization of the replica method. For Q-partite, we prepare n to the Q-1 replicas and impose non-trivial permutation on them as follows. For usual Q equal 2 case, we glue replicas along the subregion A. But for Q equal 3 case, we glue replicas along A in the vertical direction, while along B in the horizontal direction. And this prescription can be generalized to arbitrary Q and N. And since mulch entropy contains the lower partite entanglement, we need to subtract them. And for Q equal 3 case, we can define genuine tree entropy as shown here. And also for Q equal 3 case, the holographic dual of tree entropy is given by the trivalent geodesic length. Here I show two examples of BTZ case and the folding particle geometry in the Poincare coordinate. And now we are considering the local heavy quench whose gravity dual is a massive folding particle. And since the particle trajectory can be mapped to the origin of the global coordinate, the back-reacted metric can be written in the BTZ coordinate. And the resulting tree entropy is expressed in terms of the invariant length Lij, which depends on the winding number m. And by subtracting the bipartite entropies and also vacuum genuine tree entropy, we obtain this result. And the vacuum subtracted genuine tree entropy arises from the mismatch between the windings for the trivalent geodesics and those for pairwise geodesic. And this is a corresponding plot. And the purple curve shows the genuine tree entropy. And we found that the rising point and the falling point corresponds to the bipartite transitions. And also two cusps correspond to the tripartite transitions. And these transitions comes from the winding saddle transitions. And we can understand this behavior from the gravity picture. First, the falling particle crosses bipartite geodesic and then trivalent geodesics twice, and finally another bipartite geodesic. And these crossings correspond to the rising point and the two cusps and the falling point respectively. So we can conclude that the genuine tree entropy is governed by the saddle transitions. On the CFT side, we consider two heavy operators and three twist operators. And to obtain the replica partition function, we calculate the corresponding 5-point function. In this calculation, we use the heavy light vacuum Broca approximation. More specifically, we use Möbius map and the uniformization map. And since the uniformization map is multi-valued, so we should minimize over the branch choices, which corresponds to the winding numbers in the holographic calculation. And finally, we exactly reproduce the holographic results. And okay, so that's all for my talk. So if you get interested in my talk, please come to my poster. Yeah, so I will also have a poster presentation. So thank you very much for your attention.
Thanks for the opportunity to give a talk here. My name is Zixiao Huang, and I'm a PhD student at Fudan University. And as you can see from this big title here, it's from anomalies, but I'm actually talking about why anomalies governs the universal defect energy and entropy. So in the following, I will explain this in details. And before I move ahead, my supervisor, Professor Yang Zhou, will give a formal talk on this work on Friday afternoon. So you're welcome to attend his talk for more details. Okay. To begin with, let me just review a very basic property of a quantum field theory. So the Y anomaly, or the central charge, governs the ground state energy and the entanglement structure of a conformal field theory. And this can be understood as it counts the degrees of freedom. So for example, in a 2D CFT, the Y anomaly manifesting the trace anomaly of the stress tensor, and it governs the Casimir energy and the Renyi entropy as it appears in the overall coefficients. So now let's introduce defects, which are usually defined by non-local operators or boundary conditions in quantum field theories. And usually they can have non-trivial interaction with the ambient theory degrees of freedom. And importantly, the defects can carry their own anomaly coefficients. So for example, a two-dimensional surface defect has 3 Y anomalies, which is small b, d1, and d2 here. So a very natural question is, with the defect inserted in the theory, so is there still any analogous relation between the anomaly energy and entropy? And our short answer is yes. So for a supersymmetric system, we find that defect anomaly governs the defect contribution to the Susy-Casimir energy and the Susy-Renyi entropy. So our first example is the Wilson surface in 62.0 theory. So you can see from this formula that we compute the defect contribution to the Susy-Casimir energy, and it is indeed universally governed by the defect Y anomaly B and D2 via these two special linear combinations. And this defect contribution to the Susy-Casimir Renyi entropy is also controlled by the defect Y anomaly to be minus D2 here. And by the Susy-Casimir energy, I'm actually talking about the low temperature limit of the partition function in the radial quantization. And the Susy-Renyi entropy is a generalization of the entanglement entropy. And by taking the small n goes to 1, you go back to the entanglement entropy. Okay, so to derive this formula, we use a 3-in-1 method, which combines the localization, holography, and a non-polynomial. So I'll just sketch the main ideas here. So for example, from the dimension reduction, we compute the expectation value of a Wilson loop inserted in the 5D maximum super Yang-Mills. And from the low temperature limit, we extract the defect Susy-Casimir energy. And by holography, we can compute the larger limit of the defect Susy-Renyi entropy from the probe M2 brane action on the 7-dimensional topological black hole. And these results can be cross-checked by the equivariant integral of the defect anomaly polynomial. So far I've been focused on the Wilson surface case, but the relation between the defect anomaly, energy, and entropy goes beyond these particular defect systems. So in this ongoing work, we study more defect systems. For example, the group of Witten defects in 4D n+4 super Yang-Mills, and for surface defects in 61.0 theory. And we apply our method, and we find that in these defect systems, the defect contribution to Susy-Casimir energy and Susy-Renyi entropy are also governed by the defect Hooft anomaly. Okay, so a very brief conclusion here. We found that the surface defect contribution to the Susy-Casimir energy and the Susy-Renyi entropy are universally controlled by the defect Y anomaly. And our 3-in-1 method can be generalized to more defect systems. Okay, so if you're interested, please come to my poster, and I'm looking forward to have a discussion with you. So thank you very much.
Good afternoon. Thanks the organizer for giving me this wonderful opportunity to talk about our recent work. I'm Bing Xin, a graduate student from Princeton University. And today I will talk about the duality between the two-dimensional gravitational system and boundary conformal field theory. This is the work in progress with my advisor, Juan Maldacena and Ahmed Ahmari. JT gravity is a two-dimensional model of nearly ADS2 gravity. And coupling to a conformal field theory gives the simplest control setting for quantum matter interacting with nearly ADS2 gravity. Moreover, this is a toy model to study the black hole evaporation. And we are interested in the low temperature limit, the low infrared dynamics in this case. The main thing is that under this limit, we found the CFT measurement dominates the dynamics. Furthermore, there exists an interesting emergent duality. The gravitational system is dual to the Ishibashi state. Based on this observation, we can establish the microscopic description of this two-dimensional black hole system. Let me briefly introduce the basic setting of our study. The whole space is divided into two parts. On the left half space, we have JT gravity coupled to conformal field theory. And on the right half space, we have the conformal field theory living on the flat space. And the middle boundary is transparent for the conformal matter. And we can write down the action of the full theory. The first line is the usual JT gravity. And the second line comes from the Polyakov anomaly action, where chi is the wire factor. And we can also write down the black hole evaporation formula written in the equation 1. The term inside the bracket is the ADM energy of the gravitational system. And the right-hand side is the net energy flux through the boundary. And at equilibrium, the left-hand side of the equation is 0. So T plus plus equals to E T minus minus. This is the incoming energy flux equals to the outgoing energy flux. And in CFT language, this is exactly the conformal boundary condition, the reflective boundary condition for the stress energy flux written in the equation 2. And the solution denoted by double cat I of this condition inside one Virasoro representation is called the Ishibashi state. So the main question we want to ask is that which boundary CFT state does the gravity prepare? And to solve this question, we need to evaluate the action more deeper. For the CFT part, you need to deal with the so-called conformal welding problem. And after you taking this, this can be written in terms of in the equation 3, written in terms of the theta, the boundary reparametrization, and the conformal map F. And F also depends on the theta. And for the JT part, we are both very familiar with. We just reduce this action to the 1D boundary Schwarzschild, written in the equation 4. And it is also easy to verify that the settle is exactly theta equals to phi, and we can perturbably expand this action to the quadratic order of the epsilon. And at low temperature limit, the beta is very large. The CFT action dominates the dynamics, and we can approximate one loop effective action by dropping the Schwarzschild part. Then under this limit, we can answer the question we raised before. The gravitational disk is equivalent to the vacuum Ishibashi state imposed on the Green boundary, shown in the picture. And we can check this duality by computing the coordinates of operators inserted in the above. And just give you an example, we can insert two identical CFT operators in the buff, and we can compute the gravitational path integral. And we can write down the gravitational path integral gives the correction in equation 6, and chi is the conformal cross ratio. And this is exactly the 4-point vacuum reversible conformal block at order 1/c. And from the BCFT perspective, we need to compute the correlation shown in this inner product. And applying the doubling trick, this result is also vacuum reversible 4-point conformal block. And let me end my presentation with some final comments. First is that we check this correlation perturbably in order 1/c, but this is true to all orders. And second, we can generate other Ishibashi state via deforming the gravitational disk with primary operators. And last but not least, we can generalize this discussion to other geometries, especially the wormhole, the double trumpet case. And this provides a way to understand the idea wormholes comes from the ensemble average. And thank you for your attention.
Hi, everyone. Thanks for everyone making this conference possible. I'm Jamie Ling from Imperial College. Today, I will share our works in constant truncation of supergravity on half PPS background. Constant truncation is one in which all lower dimensional solution uplift by truncation ansatz are exact solution of higher dimensional supergravity. So it's an important tool to generate new supergravity solution. In our work, we construct constant truncation from 11D and type 2 supergravity to lower dimensional supergravity living on the volume of half BPS brane. To be concrete, let's see the metric. If you are familiar with BPS brane background, it's just a deformation. Here, the curve metric G mu nu is along the BPS brane volume, and it serves as the metric of lower dimensional supergravity. And H is a general harmonic function defined with respect to the delta function in the transfer space. Also, the transfer space is conformally flat and non-compact. The constant truncation emits a natural discretion in terms of exceptional general geometry. Exceptional general geometry manifests the U duality by enlarge the tangent space that we're usually working on to something called exceptional general geometry that in the fundamental representation of corresponding exceptional group. In such language, all those BPS brane background emit a torsion-free spin N structure. The spin N, the N is the number of the transverse direction. The spin N structure has nothing to do with the SON structure in the transverse space. Instead, it's embedded into the exceptional group through a subgroup spin N. So you can only see the spin N structure by considering the exceptional general geometry, but not in the normal geometry. At least I can't. Given the spin N structure, you can find all the constant truncation by expanding the higher dimensional fields in terms of the singlets of spin N, because singlets times singlets are always singlets. And I should emphasize that the flux in the BPS brane background play an important role for the spin N structure to exist, and hence the truncation. As a direct application, we consider black brane solution living on the volumes of gravity and uplift them. Through this way, we find a new class of intersecting brane solution where there's one of the branes fully localized. Let me give you an example. The D3 brane D3 F1 D5 F1 D3 brane system. Here we choose the D5 brane to be fully localized, and the left F1 D3 brane are smearing with each other, and it's in the usual sense of intersecting brane solution of supergravity. And you can understand this intersecting brane solution as a uplift of black hole living on the D5 brane volume where there's a 61,1 supergravity. And another way, you can think the black hole as the intersection of F1 D3 brane with the D5 brane. Also, we know that the near horizon limit of black brane solution are ADS type. So we can also construct ADS3 times S3 solution by going to the near horizon limit of black string living on the D5 brane volume into A. Up to now, I didn't mention any details of the truncate supergravity. They are half supersymmetry and mostly minimal. It sounds a little bit boring, but more meta multipliers are allowed if we choose some specific harmonic function. And also, it's one of the few known cases where the fluxes appears in the background play an essential role in defining the structure. Another case could be sphere reduction where there emits a generalized parallelizable. That's why you can reduce sphere and get a maximal supergravity. There are some interesting future direction. One of it would be considered brane located at conical singularity. The truncation to the volume of such brane would emit less supersymmetry. Also, there's no classification of truncation to half maximal supergravity. It would be interesting to classify it with exceptional general geometry. Thanks for your attention. If you have any interest in of the details, just come to my poster. Thank you.
All right, good afternoon, everyone. I'm Guan Yu, or Ricky. Today, I'm very happy to be talking about a work in progress with my advisor, Gary Horowitz, on a new gravitational instability of 5-dimensional extremal Reisner-Nordstrom black holes. So, black objects are known to possess some instabilities, perhaps the most well-known of which is the Gregory-LaFlamme instability, which basically states that for extended black objects like black strings, black brains, when they're very stretched, there are perturbations that can grow, and the horizon can have ripples, and they can pinch off. But so it's a very strong instability, but it tends to happen only for non-extremal black objects. On the other hand, for extremal black holes, there's another kind of instability. That's the Arataki type instabilities. But this instability is a much milder instability. There's no horizons becoming singular, pinching off, nothing crazy like that. But today, what we're going to talk about is an instability for an extremal black hole, but it's much stronger than the Arataki type instabilities. More like a Gregory-LaFlamme. So there's supposed to be an animation. I don't know why it's not working. But so essentially, the story is that let's go to 5 space-time dimensions. So there are 4 spatial directions, 2 orthogonal planes in which you can add angular momenta. And the extremal horizon S3 is squashed, and the squashedness depends on the ratio of the angular momenta you add in the 2 orthogonal planes. So if the ratio is very large or very small, or in the extreme case, if you are adding only 1 angular momentum, then the horizon becomes singular. So this is not only a singularity of the horizon, but it's also an instability in the sense that this perturbation depends only on the ratio and not on the magnitudes of the angular momenta. So in particular, if we're adding an arbitrarily small angular momentum in one of the orthogonal planes, the horizon becomes singular. So I want to point out that, of course, even in 4D, say, familiar Kerr-Newman, when you're adding angular momentum, the metric receives corrections. But what we're saying is that, say you're having an order epsilon angular momentum, the metric receives order epsilon square corrections, but on top of that, there's a weird order 1 constraint, and that depends on the ratio of the angular momenta, and that is what's responsible for the instability that we find in 5 dimensions. So now you can ask whether there's any dynamical obstruction that prevents you from spinning up a black hole in only one of the orthogonal planes. And the answer is no. So indeed, you can, for example, send in scalar fields, and you can have tunable parameters to control the energy angular momenta that you send into the black hole to be whatever you want. And that works for whatever dimension, 4, 5, 6, and there's nothing special in 5. So indeed, you can spin up the black hole in only one of the orthogonal planes. So you might wonder how you know that the black hole you produce this way is indeed extremal. If you worry about that, there's a sort of recent framework known as critical collapse, which essentially has some continuity argument that ensures that you can get an extremal black hole. So we also studied the situations in higher dimensions, and to your surprise, we did not find such an instability in d equals 6 and higher. So in those higher dimensions, you can consistently solve the equations with only 1 angular momentum, and there's nothing strange, nothing unstable. So the instability only happens in 5 space-time dimensions, which is something we'd like to understand better. But of course, on top of that, there are other things we would like to study. For example, like what people have done for Gregory-LaFlamme, we would like to understand maybe what's actually going to happen by, say, having a fully nonlinear numerical evolution. And there are other regimes of interest, which, for example, in 5D, there's this, or higher D as well, there's a general rotating black hole known as the Myers-Perry black hole. And that one, in the extremal limit with only 1 angular momentum, also has a singular horizon, but that's milder. It doesn't have an instability, but we would like to see whether the singular horizon we have is connected maybe to this Myers-Perry case in some sense, and perhaps even better to have a full phase diagram of these 5-dimensional black holes. And many other things. It's a work in progress, so I very much welcome feedback and comments, so please come to the poster for further discussions. Thank you very much.
Okay.
Thank you very much for giving me this opportunity. My name is Hyunwoo Oh from Seoul National University, and today I'd like to present my work on ABJ theory based on the paper titled BPS phases and for treating higher spin holography. Okay, let me briefly outline the background for my work. The discovery of black hole entropy motivates us to study black hole microstage, and thanks to ADS CFT, we can study black hole microstage from the CFT side. And its supersymmetric theories, BPS stage are in one-to-one correspondence with two cohomology classes. And it has been conjectured that the Furtwängler stage, which become non-trivial cohomology due to trace relations, will correspond to the black hole microstage. Also, in larger limit, we can use matrix model technique for the gauge theory, and the confined phase corresponds to the black hole phase. We apply these two techniques to ABJ theory. ABJ theory is 3D n equals 6 un times 3m Chern-Simons Mayer theory. There are 4 chiral multiplets. Two of them are in the bifundamental representation, and the others are in the anti-bifundamental representation. This theory is due to Vasudev higher spin gravity on AJ4 in the limit. And in our work, we set m to be 1, so this theory becomes a vector model, and all letters in the chiral multiplet are either column vectors or row vectors. There are 12 Poincare supercharges and 12 conformal supercharges, and we pick one pair of them and study BPS stage preserving them. At non-zero hooped coupling, only the graviton multiplet remains BPS, and most of free BPS become non-BPS at non-zero hooped coupling because they acquire anomalous dimensions. However, this non-BPS stage form multi-particle BPS bound stage like OR through m equals 1 trace relations. Also, we constructed the explicit n equals 2 for Church stage, which we interpret as a black hole microstage or heavy operator. Okay, moving on to the next point. We want to see larger limit of the superconformal index. We turn off the R symmetry fugacities and interpret the fugacity for charge E plus J as the inverse temperature beta. In larger limit, without any additional scaling, the log jet diverges as 1 over beta squared. Since the gas of gravitons will give only 1 over beta, this stronger divergence signals the infinitely many higher spinning particle BPS particle species. And the operators OR, which are already found, provide the explicit examples of such stage. Next, we studied the index using a matrix model for holonomy eigenvalues. In the larger limit, the eigenvalue distribution is described by an continuous eigenvalue density, and the log jet can be written as an integration. For non-trivial settle, 2 terms have to be balanced, so we fix n beta to be finite. And we solved 1 cut at 2 cut solution, and for 1 cut, we could analytically evaluate the free energy. From the free energy of 1 cut, we performed Legendre transform to obtain J entropy for fixed charge J. And for the charge below JC, the 1 cut settle no longer exists. This happens because the cut of the settle hits the singularity at pi over 2 of the external potential. Also, if we formally continue the free energy, the entropy becomes negative below a certain charge J0. And equivalently, in the grand canonical ensemble, the 1 cut settle exists only above a critical temperature Tc. So this 1 cut settle is connected to the Cadel limit, high temperature, but it's not connected to lower temperature, uniform density. So this motivated us to find another solution. First, we compared the contribution to log jet from one curve eigenvalue on the cut and psi times pi. The eigenvalue at pi corresponds to an eigenvalue instanton. And below a certain temperature, the contribution from the contribution from eigenvalue instanton becomes larger from the contribution from the 1 cut. So the eigenvalue instanton lowers the free energy, and creating a new cut is preferred. So at low temperature, the 2 cut settle continuously approach the uniform settle. This figure on the right-hand side shows an example of the 2 cut eigenvalue distribution. And additional to the continuously approaching, the asymptotic behavior of free energy of the 2 cut solution also agrees with the uniform settle. Okay. So thank you very much for your attention, and I hope to see you at the poster session. Thank you.
Okay, hi everyone. Thanks to the organizers for giving me the opportunity to speak. So I'm Ahmed. I'll tell you a little bit about infinite dimensional algebras in ADS4 and light ray operators in CFT3. So Andy gave a very nice talk this morning about the paper, so this will be your chance to get the 5-minute elevator pitch. So the basic premise is that, as we all know, holography offers the most promising framework in trying to understand quantum gravity. The problem is that it works very differently depending on the asymptotics of your space-time, whether you're in ADS, DS, or flat space. So the main motivation is to try to look for universal aspects that connect the holographic framework across different asymptotics. So on the one hand, we have holography in ADS, which is a very well-developed story in the form of the ADS-CFT correspondence. On the other hand, there's been a lot of effort in recent years trying to understand what holography might possibly look like in the context of flat space. And the central theme of this line of work has centered around the very rich infrared dynamics of the flat space S matrix, which was shown to be governed by the so-called soft algebras, which are basically infinite dimensional algebras that control the soft modes on scry, or equivalently, the collinear divergences of the S matrix. These algebras are known as the S and the W algebra, respectively, for the case of gluons and gravitons, respectively, and they take the form written on the slide here. Very interestingly, these authors recently discovered a deformation of these algebras, which is parametrized by the cosmological constant. So because ADS holography is so well understood, the main question we tackle is to try to look for the holographic realization of these algebras within the context of ADS-CFT. Finding such a common thread could teach us about both sides. So for example, despite its comprehensiveness, there are still some mysteries in ADS-CFT that are better understood in flat space, such as defining self-dual theories and computing their correlators, amongst other things. Conversely, one could use the full might of ADS-CFT to teach us about the ingredients of the flat hologram, addressing puzzles like what else is needed beyond the soft physics in order to encode the full dynamics of the bulk theory. So our main result is that we actually uncover a copy of this S algebra in 3D CFTs. So here I've rewritten the algebra in the blue box just to flash our main result. Don't worry too much about all the details of the indices. Just think of a generalized cat smoothie with a little bit more indices. So one of the unexpected things we discover is actually how universal this algebra is. So it exists in any three-dimensional CFT which has a conserved, an n-abelian conserved current. So it goes beyond holography, but of course for holographic CFTs, this is precisely the algebra of suitably soft operators in ADS4, as I'll explain in a minute. This algebra is also infinite dimensional, so one of its generators, one of its labels P, which measures basically the scaling dimension of the generators, takes on all the positive half integers starting with 1. And in fact, it's an entirely non-perturbative algebra within the CFT. So it's an exact infinite dimensional algebra in any 3D CFT with an n-abelian conserved current, which is pretty cool. And finally, there's a completely analogous story where you substitute the stress tensor for the current, and you end up with a copy of the lambda deformed W algebra in the CFT. So the technology behind this result is that basically this is the algebra of light ray operators in the CFT. So what is that? Basically, you start with your conserved current, and then you smear it along a certain null geodesic in the space-time where your CFT lives. This gives you a non-local operator called the light ray operator, whose properties are very well studied. In particular, it transforms as a CFT primary. The leading generator of the algebra, the one with the lowest scaling dimension, is precisely given by this light ray operator, and its commutator is completely fixed in terms of the ward identity of the global charge in the CFT. The sub-leading modes, the ones with higher scaling dimension, are then given by three-dimensional conformal descendants of this light ray operator. So because we're in a 3D CFT, the algebra of descendants is completely fixed by the algebra of the primary light ray operator, and the full conformal multiplet basically obeys the S algebra. I also wanted to briefly mention the associated bulk story. So first, ADS4 is Weyl equivalent to 4D flat space. And the basic point is that there's a specific Weyl transformation such that the boundary of ADS intersects the boundary of flat space along some null rays. So then you start with the soft generators in flat space, which are given by integrals of the field strength tensor along some null rays in scry. And then you push them basically to where the scry plus intersects with the boundary of ADS. Then, using the ADS-CFT extrapolate dictionary, you precisely land on these light ray operators. But of course, as I mentioned, the resulting light ray algebra is completely independent of holography and of this geometric construction. So to quickly recap, we have infinite dimensional algebras that arise in 4D holography across different asymptotics, some of the implications of which we're currently investigating. Thank you very much.
First, I would like to thank the organizers for giving me this opportunity to present in the string conference. So, good afternoon, everyone. My name is Jiayue Yang, and I'm a second-year PhD student from IQC University of Waterloo and the Perimeter Institute. And today, I would like to talk about our recent work on relativistic quantum information meets holography. And this work is collaborating with Human, PhD just graduated from our group, and Ming Zhang, a postdoc from our group, and now in Jiangxi Normal University, and my supervisor, Professor Robert Mann. So you may ask, what is relativistic quantum information? It is a field that studies how relativistic effects and gravitational effects affect the quantum information protocols, and how the quantum detectors can be served as an operational probe of the nature of space-time. So probably one of the most famous examples is the entanglement harvesting, where quantum detectors can acquire entanglement from the vacuum state of a quantum field. And recently, this group shows that another kind of quantum resources, which is called magic, can be harvested in a four-dimensional Minkowski space-time. And our group showed that the magic resources can also be harvested in general dimensional anti-de Sitter space-time and also in conformal field series. So we start with a detector that has 3 energy eigenlevels, and in the ground state, K 0, and the field is a scalar field that is in a vacuum state. And we consider this detector field interaction, where lambda is the coupling strength and chi is the switching function. Mu is the monopole operator describing the state transitions of the detector, and phi here is the field operator. And after the detector field interaction, we trace out the degrees of freedom of the quantum field and get the reduced density matrix of the Q-tree detector, where Q is the transition probability to the excited state and beta is the coherence. And we can compute magic from this reduced density matrix, which is just determined by this Q and beta, and it is actually from the computation of Q and beta. And we showed that although in curved spacetime, we can still obtain the analytic results of the transition probability and the coherence for this Q trait in anti-de Sitter spacetime, where the expression of Q is given by this, and the expression of the coherence is given by this. And you can observe that they exhibit very similar structures. The only difference is the factor of 2 and the factor in the exponents. And the magic is come from the computation of these two. And only when the coherence is selective enough, so we can obtain the magic from this quantum field. And here we plot the harvesting magic as a function of the energy gap. You can see that there is an optimal energy gap, and for stronger curvature and larger space-time dimension, the magic harvested from the quantum field will be suppressed. So we can use this Q-trait detector as a probe of the space-time curvature and dimension. And since we are interested in holography, we also consider the magic harvesting in CFTs. So in ADS-CFT, we have the field operator correspondence, where a bulk scalar field phi is due to this CFT prime operator O with the scaling dimension delta. And so we have this mass scaling dimension relation. And this has 2 solutions because we consider a conformally massless scalar field. So we are in the BF window. So we have these 2 admissible quantizations, where delta plus is a larger scaling dimension and the delta minus is a smaller dimension. And we can also obtain the analytic results for this transition probability and the coherence in CFTs. So we have the expression of Q and beta, which is also similar to the ADS case. And we can plot the magic in CFTs. We can also see that there is an optimal energy gap. And for larger scaling dimension, we have smaller magic. So we can use this Q-trait detector as a probe of this CFTs. And this is also consistent with the bulk ADS side. That's all. Thank you.
Hi. Hi, my name is Xuyang Yu. And since I'm the last Gong Show speaker of the day, I will start with the opening question in a big picture. Since gravity has diffeomorphism invariance, it's intrinsically non-local. So when and how is quantum gravity equal to local QFT? This is a joint work with Molly, Dang, and Ying at UC Santa Barbara. Let's look at the flow chart on the right. The full quantum gravity in asymptotically de Sitter spacetime is a broad dream, but of course, it's extremely difficult. So we go to a more tractable model that is perturbative quantum gravity around de Sitter spacetime with no gravitational back reaction. So you may ask, how is that different from QFT in a fixed de Sitter spacetime? The key input from gravity, here I'll point out, is coming from total gravitational charge equals 0. So you start from a QFT state. You can impose such a constraint called linearization stability constraint. Basically, the states has to be invariant under any symmetry transformation imposed from gravity. Then you can create a physical state in quantum gravity such that they are stable under higher order corrections. Okay. I will skip the review of global de Sitter spacetime, but there are a few points you should keep in mind. Is that de Sitter, unlike ADS or flat spacetime, it does not have a spatial boundary. So we need a asymptotic anchor to define operators. Another point is that gravity impose in de Sitter spacetime, we impose the de Sitter isometry charge. So unlike CLPW, where they impose or mainly study the time translation real group, here we consider the full de Sitter isometry group, SOD(1). To recreate local QFT, then we need to find a way to both impose this relational observable and also define the physical states. Now the technique we will use is called group averaging. Group averaging gives us symmetry invariant states. Given a QFT state psi, we integrate over all possible group transformations written in U of G, so you produce a state that is invariant under any further group transformations. Now there are some subtleties about the normalization of the produced state that I'm studying in ongoing work with my advisor, Don. Then you consider a reference. Okay. Given two QFT, say phi and psi, now you can think of them for simplicity. They are free scalar fields. Choose one to be a reference field. Reference field to be localized in a reference wave packet psi 0. Then you can define the QFT operator in such a way, tensoring the reference state and then do a full group averaging. Now the detail of our work is to study this group averaging kernel, psi u psi, and to study how sharply peak it is. And there are also earlier reference you should check out Marv Morrison a long time ago. But this observer relational correlator is a new ingredient. I will save you from the trouble. I will emphasize that our result applies to all dimensions, but there's a example calculation in 1 plus 1D. If you look at the diagram on the right, basically, diagrammatically, you will say that the QFT is well recreated in the center region of this conformal diagram, and we quantitatively compute the time range. I will emphasize that it works for all dimensions. Now, I will leave this with the punchline of our talk, is that using the technique of group averaging, we can reproduce local QFT from de Sitter quantum gravity in a control region. And I will save you the trouble from the extension to cosmology relations, since the whole talk will serve as a hook for you all to check out our paper. Okay, thank you for your attention.
Okay, so this concludes our very nice Gong Show session, first Gong Show session. We will have another Gong Show session tomorrow. Let's give a final round of applause to all Gong Show presenters today. So now we have a poster session. We received more than 120 posters. So please follow to the coffee break area to check posters for all nice young scientists. Thank you.